in separately excited DC generator, the excitation is separate, which is independent of terminal voltage of any kind of load. In separately excited DC generator, the excitation is separate, which is independent of terminal voltage of any kind of load. See, in a separately excited DC generator, we are going to give the excitation to the field winding separately. With the separate DC supply, we are going to give the excitation to the field winding. So it is called as a separately excited DC generator. So in separately excited DC generator, the excitation is separate, which is independent of terminal voltage of any kind of load. So in separately excited DC generator, the excitation is separate, which is independent of terminal voltage of any kind of load. In shunt DC generator, field winding has high resistance, which is 30 to 200 ohm. So in a shunt DC generator, field winding has high resistance, which is 30 to 200 ohm. The huge turns made of thin wire. The terminal voltage is nearly constant for any kind of load from no load to full load. So IF is constant and phi is a constant from no load to full load. See, in a shunt DC generator, the field winding has a high resistance, which is 30 to 200 ohm, with a huge turns but made of thin wire. So turns are huge means the wire is very thin, because R is equal to rho L by area. As area decreases, the resistance increases. So here we are going to use huge number of turns. As length increases, the resistance increases. As the area decreases, the resistance increases. So therefore, they will have huge number of lengths or huge number of turns. The area is less, so they have huge amount of resistance, and the terminal voltage is nearly constant for any kind of load from no load to full load. The variation of the terminal voltage from no load to full load is almost constant. So IF is also constant, and the flux is also constant from no load to full load. So this is basically the principle of the DC shunt generator. So DC shunt generator has the field winding with a huge amount of resistance, like 30 to 200 ohm. So basically it has a large number of turns, means large number of length, and it has basically, you can say that it has less number of area, has less thin wire. Basically it has thin wire means less area. So R is equal to rho L by area. As L increases and area decreases, the resistance will increase. So from no load to full load, the terminal voltage is almost constant. So as terminal voltage is constant, IF is constant. So flux is also constant from no load to full load in case of this DC shunt generator. Whereas in series DC generator, phi SC is proportional to IA only up to saturation. So field winding resistance is of thick wire with few turns. So here in the DC series generator, the flux is directly proportional to armature current. So this is the case only up to saturation. After that, flux is equal to constant irrespective of the current IA. So therefore here we are going to use a field winding of thick wire. So we are going to use a thick wire. Thick wire means area is higher with a less number of turns. So R is equal to L by A. As the area is a thick and less number of turns, the overall resistance is very less. So resistance of series winding is very less when compared to shunt field winding resistance. So this is a very important point. It has a thicker area with less number of turns. So it has less amount of resistance, and the flux is directly proportional to armature current only up to saturation. After that, flux is equal to constant irrespective of the current IA. So we can say that in a DC series generator, phi S is directly proportional to IA only up to saturation. After that, flux is equal to constant irrespective of the current IA, and the field winding resistance is basically made of thick wire with less number of turns. So therefore, as less number of turns means length is less, and the area is thick turns means the area is higher. So overall resistance is very less. Cumulative compound DC generator. Cumulative compound DC generator means the overall flux, the net flux is equal to shunt flux plus series flux. It is a cumulative means it is a addition. It is addition of the shunt flux and the series flux. If phi SC increases, so if phi SC, or you can say that simply, if the load increases, then ISC increases, then flux increases, then net flux increases, then net EG increases. So therefore terminal voltage increases. So whenever the load increases, so this is the consequences that are going to happen. So whenever the load increases, what is going to happen? Whenever the load increases, the load current increases, then phi SC increases, then phi net increases, then EG increases, then increases. So this is in case of the cumulative compound DC generator. So whenever the load increases, then ISC increases, so phi SC increases, so phi net increases, so therefore EG increases, so therefore V increases, so whenever the load increases. Whereas in the differential compound DC generator, phi net is equal to phi s minus phi sc. So whenever the load increases, the ISC increases. So phi sc increases, the overall flux will decrease. So Eg decreases. So V also decreases. So this is whenever the load is increases. So therefore, we can say whenever the load increases, the terminal voltage increases in the cumulative compound DC generator. But whenever the load increases, the terminal voltage will decrease in case of the differentiable compound DC generator. So this is a very important thing that you always need to analyze. So whenever the load increases, the the terminal voltage also increases for the cumulative compound DC generator, and whenever the load increases, the terminal voltage decreases for the differential compound DC generator. So in a cumulative compound DC generator, net flux is equal to phi SH plus phi SC. So as the load increases, then ISC increases, so phi SC increases, so net flux increases, so Eg increases, so V increases. So whenever the load increases, the terminal voltage will increase in the cumulative compound DC generator. Whereas in differentiable compound DC generator, the net flux is equal to phi SH minus phi SC. So as the load increases, then ISC increases, so phi SC increases, so net flux decreases, so Eg decreases and V decreases. So therefore, whenever the load increases, the terminal voltage will decrease in the differentially compound DC generator. The load current and load voltage of both long shunt and short shunt is nearly same for a given load. The load current and load voltage of both long shunt and the short shunt is nearly same for a given load. See, there is a small amount of variation, but it is almost constant. The load current and load voltage for both long shunt and short shunt is nearly same for a given load. See, a small amount of variation of load voltage and load current happens if you keep that load for the long shunt and also for the short shunt. So this is a very important point. The load current and the load voltage of both long shunt and short shunt is nearly same for a given load. So on pole first we will own the shunt field winding, and then we will own the series field winding, because in a compound DC generator, series winding will carry load current. So series field winding will carry the load current. So for cooling purpose, we keep series field winding outside the shunt field winding. So if you see basically a pole on which we are going to own the shunt field winding, and over that we are going to own the series field winding, because in compound DC generator, series field winding will carry the load current, and for the cooling purpose we keep the series field winding outside the shunt field winding. So this is a very important point. So you can see clearly that here, suppose in case of a compound DC generator, the series field winding will contain the load current. So on a pole, first we are going to own the shunt field winding, and on that we are going to own the series field winding, because series field winding is going to contain the load current, which is very high. So we keep on the shunt field winding for easy cooling purpose. So therefore, on pole first we will own the shunt field winding, and then we will own the series field winding, because in a compound DC generator, series field winding will carry load current. So for cooling purpose we keep the series field winding outside the shunt field winding. See, at no load, the series flux is nearly equal to 0, because as whenever there is no load, current is equal to 0, so phi S is also nearly equal to 0. The compound short shunt and long shunt acts like a shunt now. So therefore, at no load, when phi S is nearly equal to 0, the compound short shunt and the long shunt is going to act like a shunt machine itself. So like a shunt DC generator. So at no load, the compound short shunt and the compound long shunt is going to behave like a purely shunted machine, like a shunt machine itself, because at no load the current is equal to 0. So therefore phi S is equal to 0. The compound long shunt and the compound short shunt is going to behave purely like a shunt DC machine. So V rated is less than V no load. This for the under compound machine. So we can say that under compound is the no load voltage. If the no load voltage is, if the rated voltage, if the voltage at rated load is less than no load voltage, it is said to be a under compound machine. Whereas at level compound machine, if the voltage at rated load is equal to voltage at no load, it is said to be level compound machine. And similarly, the voltage at rated load, if it is higher than the voltage at no load, it is called as the over compound machine. So at rated load, the voltage at the rated load, if it is higher than the no load voltage, it is called as over compound machine. Whereas if the voltage at rated load is equal to no load voltage, it is called as the level compound machine. if the voltage at rated load is lesser than the no load voltage, this is called as the under compound machine. So if the voltage at rated load is greater than voltage at no load, this is called as over compound machine. If the voltage at rated load is equal to voltage at no load, this is called as level compound machine. If the voltage at rated load is less than voltage at no load, this is called as the under compound machine. It requires some essential conditions to be satisfied for the build-up of voltage in self-excited machines. These are for a shunt generator. So these are for a shunt generator. So here basically there are some essential conditions. So basically there are some essential conditions that must be satisfied for a build-up of voltage in self-excited machines. And these are some of the conditions for a shunt generator. So it requires some essential conditions to be satisfied for the build-up of voltage in self-excited machines. These are for a shunt generator. For a shunt DC generator, which are the poles should contain residual magnetism, field winding and armature winding should be correctly connected so that initial MMF had a residual flux. So the resistance of the field winding must be lesser than the critical resistance, and the speed of the generator should be greater than the critical speed. So best condition is no load, proper brush contact for pulling for collecting the current. You can see that it requires some essential conditions to be satisfied for the build-up of voltage in self-excited machines. These are for a shunt DC generator, which is the pole should be contain the residual magnetism, field winding and the armature winding should be correctly connected so that initial MMF add the residual flux. The resistance of the field winding must be lesser than the critical resistance. Speed of the generator should be greater than the critical speed. Best condition is no load and the proper brush contact for collecting the current. So these are the essential conditions for build-up of voltage in a self-excited machines for a DC shunt generator. The poles should contain the residual magnetism, field winding and the armature winding should be correctly connected so that initial MMF is add the residual flux. And the resistance of the field winding must be lesser than the critical resistance, and the speed of the generator should be greater than the critical speed. And the condition is at the no load and the proper brush contact for the collecting the current. So proper brush contact for the collecting the current. So these are the essential conditions that are required for building up of voltage in the self-excited machines in the DC shunt generator. Initially the pole should have the initial magnetism. So it should have some initial residual magnetism, and the field winding and the armature winding should be connected in such a manner. So whatever the initial MMF, it should add the residual flux. And the field winding resistance should be lesser than the critical resistance, and the speed of the generator should be greater than the critical speed. The best condition is basically at the no load condition and the proper brush contact for collecting the current. So these are the conditions that should be maintained. Then only a voltage is going to get built up in the self-excited machines. So the essential conditions to be satisfied for building up of a voltage in self-excited machines. So these are for a shunt generator, shunt DC generator. The pole should contain residual magnetism, field winding and the armature winding should be correctly connected so that initial MMF add the residual flux. The resistance of the field winding must be lesser than the critical resistance. Speed of the generator should be greater than the critical speed. Best conditions are the no load and the proper brush contact for collecting the current. So these are the essential conditions for building up of voltage in the self-excited machines. Manufacturer make sure he will make the residual flux in the poles for self-excited machines by a process called the field flashing. So manufacturer make sure he will keep the residual flux in the poles for self-excited machines by a process called the field flashing. So suppose if any pole doesn't have any, if it doesn't have any magnetism, so with the help of this field flashing method, we can keep the residual magnetism in these poles. The manufacturer is going to make sure that he will keep the residual flux in the poles for self-excited machines by a process called the field flashing. So with the help of field flashing, we can keep the residual magnetism in the poles. So manufacturer is going to make sure he will keep the residual flux in the poles for self-excited machines by a process called the field flashing. Also the characteristics of separately excited machine is same as shunt machine characteristics. So also the characteristics of separately excited machine is same as for shunt machine characteristics. So if you go for the shunt machine or whether you go for the separately excited machine, both will have the same graph at the no load condition. So therefore, also the characteristics of separately excited machine is same as the shunt machine characteristics at the no load. So also the characteristics of separately excited machine is same as that of the shunt machine characteristics at the no load condition. So critical resistance is defined as the maximum resistance of the field winding above which the generator will not build up voltage. Practically, it is figured out by drawing OCC at a given rated speed of generator and drawing tangent to OCC from origin, and slope itself is critical resistance. So this is a very important point. Suppose if the field resistance is greater than critical resistance, then definitely these two lines, the OCC lines and the EF is equal to IF into RF, will never intersect. So there will be no induced voltage, or we can say no build-up of voltage is going to get operated, because there is no operating point. OCC characteristics of separately excited machine is same as that of the shunt machine characteristics, and the critical resistance is defined as the maximum resistance of the field winding above which the generator will not build up voltage. Practically, it is figured out by the drawing OCC at the given rated speed of generator and drawing tangent to OCC from origin, and slope itself is RC. So at a rated speed, if you operate at the rated speed of the generator, then you are going to get some curve. And if you draw a straight line, if you draw a tangent line through the OCC from origin, whatever the slope is called as the critical resistance RC. So if RF is greater than RC, there is no build-up of voltage. So RF should be always less than RC. Then only there is a point of interaction between OCC and the EF is equal to IF into RF. Then we can say that there is a build-up of voltage is going to get occur. So therefore, critical resistance is defined as the maximum resistance of the field winding above which the generator will not build up voltage. Practically, it is figured out by drawing OCC at a given rated speed of generator and drawing tangent to OCC from origin, and slope itself is RC. Critical speed is defined as the minimum speed of generator below which the generator doesn't build up voltage. All this point belongs to shunt generator only. So critical speed is defined as the minimum speed of generator below which the generator doesn't build up voltage. All these points belongs to shunt generator only. So therefore we can say that here critical speed means if you operate the generator speed less than this critical speed, then again EF is equal to IF into RF graph and OCC graph will never intersect. Again there will be no point of intersection. So no voltage is going to get induced. So therefore critical speed is defined as the minimum speed of the generator below which the generator doesn't build up voltage. All these points belong to the shunt generator only. So therefore simply we can say that always we have to operate above the critical speed but not below the critical speed. So above the critical speed only EF and RF are going to get OCC and EF is equal to IF RF graph are going to get intersect. So we are going to get a common point of intersection, and below the critical speed OCC and EF is equal to IF into RF will never intersect, and you will never get a point of operation. So critical speed is defined as the minimum speed of the generator below which the generator doesn't build up voltage. All these points belong to DC shunt generator only. So what are the concepts that I have learned up to now? I have taught up to now. It is only up to DC shunt generator only. So compound motor on no load is exactly a shunt motor. I have already told you. See compound motor. So compound motor on no load is exactly a shunt motor, because here ISC is equal to 0. So phi SC is equal to 0. So therefore the net flux is equal to shunt flux. So it is going to act like a shunt motor itself at the no load. So compound motor on no load is going to behave like a shunt motor only. So in cumulative compound motor on no load is exactly a shunt motor. I have already told you, in cumulative compound motor on no load it is exactly a shunt motor. But in differential compound motor there is phi SH minus phi SC. So keep diverter RD and make RD is equal to 0. So after voltage building, remove the value of RD. But in differential compound motor there is a phi H minus phi SC. So keep diverter RD to make RD is equal to 0. So to make RD is equal to 0, so after voltage building, remove RD. So what I am trying to say basically here, this cumulative compound machine can be operated like a shunt motor. So if you are at the no load condition, whereas here there is a, but in different compound motor the net flux is equal to phi H minus phi SC. So we have to keep a diverter. Because of series field winding, we have to keep a diverter. So whenever the RD is equal to 0, then definitely no current passes through phi SC. So current ISC is equal to 0. So it is going to act like a shunt motor. So therefore we can say that, so keep diverter RD and make RD is equal to 0. So after voltage building, remove RD. So finally we can say that, see, a cumulative compound generator can at no load can act like a shunt generator. So whereas in a differentially compound generator it can act like A shunt, it can act like a shunt generator if you keep a diverter resistor and you short it and you short that diverter resistance. So finally I can say that a cumulative compound generator can act like a shunt generator at no load condition, whereas a differentially compound generator can act like a shunt generator when you make the diverter resistance. We have to connect the diverter resistance across series field winding and make it short circuit. So therefore RD is equal to 0. So no current passes through series field winding. So it is going to act like a shunt DC generator. It requires some essential conditions to be satisfied for the buildup of voltage in self-excited DC series generator. So they are, I have already told you the essential conditions for the voltage to build up in a self-excited DC shunt generator. But now we will discuss the essential conditions to be satisfied for building up of voltage in a self-excited DC series generator. They are, the pole should contain the residual flux. This is same as the previous one. Field winding and armature winding should be correctly connected so that initial MMF and the residual flux. It is also same. The resistance of the RA plus RSC plus RL, because we always have to connect the load. For a DC series generator, always you have to connect a load. So therefore RA plus RSC plus RL should be lesser than the critical resistance. Whereas in the previous case, RF should be less than RC. But here RA plus RSC plus RL should be lesser than the critical resistance. And the speed of generator should be greater than the critical speed. This is also same as the previous one. Best condition is under load. Here we have to always keep the load. Whereas in the previous case at no load condition. And the proper best conduct for collecting the current. Only these two things are changed and remaining everything is same. Here the field resistance is nothing but RA plus RSC plus RL. Whereas here we have to operate at the load condition, whereas the previous one is at the no load condition. So these are the small two changes when compared to previous one. The some essential conditions to be satisfied for build-up of voltage in a self-excited DC series generator. They are, the pole should contain the residual flux, field winding and armature winding should be correctly connected so that the initial MMF and the residual flux and the resistance of the RA plus RSC plus RL should be lesser than the critical resistance, and the speed of generator should be greater than the critical speed, and the best condition is at the under load condition, and the proper best conduct for collecting the current. So it requires some essential conditions to be satisfied for the build-up of voltage in self-excited DC series generator. They are, the pole should contain the residual flux, field winding and armature winding should be correctly connected so that initial MMF at the residual flux and the resistance of the RA plus RSC plus RL should be lesser than the critical resistance, and the speed of generator should be greater than the critical speed, and the best condition is at the load condition, under load condition, and the proper best conduct for collecting the current. So when the generator are on no load, the armature current is negligible. So when the generator are on no load, the armature current is negligible, because for a generator at no load condition, the armature current is very less. Therefore the armature ambient flux is also negligible. So once it is loaded, the armature current will increase proportionally with load. So to produce armature turns flux, this will react with main flux distribution and produces two significant effect. So therefore I already told you, at no load condition the armature current is nearly equal to 0. So armature flux is also 0. So there is no effect on the main field flux. But at the load condition, the armature current is present. So therefore it is going to produce the armature flux, and the main field flux and the armature flux are going to get interact, and it is going to produce the two significant effects. One is called as the demagnetization, means the reduction in the main field. So reduce EG and PG. So whenever the overall flux decreases, it reduces the EG and V. As EG decreases, V also decreases. Cross magnetization means distortion of main flux, which shifts the MNA from GNA and affects the conversion process. So cross magnetization means it is going to shift for the MNA from GNA by a small angle of theta. So it is going to affect the commutation process. So these are the things that you always need to be careful. Because of armature reaction, the two things are going to happen. One is called as the demagnetization, means overall flux decreases, so EG decreases and V decreases. Cross magnetization means it is going to distort the main field flux. So then the MNA is going to shift from GNA. So this will have it is going to affect the commutation process. So this is the point that you always need to keep to remember. So whenever the generator are on no load, the armature current is negligible. So therefore the armature ambient flux is also negligible. Once it is loaded, the armature current will increase proportionally with load. So to produce armature flux, and it produces armature turns flux. This will react with the main field flux distribution and produces two significant effects. One is called demagnetization, means reducing the main field flux. So therefore, energy reduces and V also decreases. And cross magnetization means it is going to distort the main field flux. So therefore, it is going to shift the MNA from GNA. So it is going to affect the commutation process also. The effect of armature flux on main field flux is called as the armature reaction. The effect of the armature flux on the main field flux is called as the armature reaction. The effect of armature flux on the main field flux is called as the armature reaction. The effect of armature flux on the main field flux distribution is called as the armature reaction. So now the armature reaction on DC generator. In this, under trailing pole tips, the flux density increases and magnetically saturated. I have already told you, in a DC generator, whenever I am going to rotate the rotor in the clockwise direction, then definitely I have already told you that the trailing pole tips are going to get saturated, but not the leading pole tips. So therefore, in this, under trailing pole tips, flux density increases and magnetically saturated. Under the leading pole tips, the flux density decreases. If the increase and decrease are equal, there is no net reduction. But under practical conditions, poles operate the new point. With the load trailing pole tips gets magnetically saturated. So with load trailing pole tips gets magnetically saturated, and the amount of increase under the trailing pole tips will be slightly less than the decrease. This produces slight demagnetization. So due to magnetic saturation of trailing poles tips, due to distortion, there is a cross magnetization which shifts the MNA in the direction of the rotational generator. In order to improve the commutation, brushes need to be shifted in the direction of rotational generator to improve the commutation. So here, armature reaction on DC generator. In this, under trailing pole tips, flux density increases and they are magnetically saturated. Under leading pole tips, the flux density decreases. If the increase and decrease are equal, there is no net reduction. But under practical conditions, poles operate near the knee point. With a load trailing pole tips get magnetically saturated, the amount of increase under the trailing pole tips will be slightly less than the decrease. So this produces slight demagnetization. So due to magnetic saturation of trailing pole tips, so due to distortion, there is a cross magnetization which shifts the MNA direction of the rotational generator. In order to improve commutation, brushes need to be shifted in the direction of the rotational generator to improve the commutation. This brush shift will improve the commutation, but it produces an additional demagnetization. These things I have already told you. So this method was used only up to 1910. Because more the load, the MNA will fluctuate always. So because more the load, the MNA will fluctuating always. So shifting brushes always is severe pain in the neck. So what I am trying to say is very simple. See, the armature reaction on DC generator. So in this, under the trailing pole tips are going to get the flux density increases and they are magnetically saturated. But under the leading pole tips, the flux density decreases. If the increase and decrease are equal, then there is no net reduction. But under practical conditions, poles operate near the knee point. With load trailing pole, you can say the trailing pole tips gets magnetically saturated. The amount of increase under the trailing pole tips will be slightly less than the decrease. Then the decrease, this produces slight demagnetization. Due to magnetic saturation of trailing pole tips, due to distortion, there is a cross magnetization which shifts the MNA in the direction of rotational generator. In order to improve commutation, brushes need to be shifted in the direction of rotational generator to improve the commutation. This brush shift will improve the commutation, but it produces an additional demagnetization. This method was used only up to 1910 because more the load, the MNA will fluctuate always. Shifting brushes always is severe pain in the neck. So finally what I am trying to say, whenever, let me assume I am going to take a DC generator. If I am going to rotate in the clockwise direction, I have already told you, under the trailing pole tips, the flux is going to get increase, and under the leading pole tips, the flux is going to decrease. So the increase and decrease are same, then there is no net reduction in flux. Practically, the poles are going to operate at the P point. The increase at the trailing pole tips is lesser when compared to decrease. So therefore, the overall flux is going to get decrease its magnetization. So this is called as a demagnetization. And because of the waveform of the flux is not a same one, it is going to distort. So therefore the MNA is going to shift its axis from the GNA. So therefore we can say we have to shift the brushes to the MNA. So by that completion is going to get improved. But if you do that, there is again further increase of demagnetization effect is going to get increased. So therefore here whenever the load increases, the MNA is going to shift its axis. So always you have to shift the brushes in the direction of MNA. So this was done only up to 1910. So after that they have used another methods to make it very easier fashion. So therefore, whenever the load changes, the MNA shifts. So if you do the process of shifting, it's a very severe pain in the neck. So finally I can say that the armature reaction on DC generator. In this, under trailing pole tips, the flux density increases and magnetically saturated. But under the leading pole tips, the flux density decreases. The increase and decrease are equal. There is no net reduction, but under practical conditions, poles operate near the key point. So with low trailing pole tips gets magnetically saturated, the amount of increase under the trailing pole tips will be slightly lesser than the decrease. This produces slight demagnetization due to magnetic saturation of the trailing pole tips. So due to distortion, there is a cross magnetization which shifts the MNA in the direction of rotation of generator. In order to improve the commutation, brushes needs to be shifted in the direction of rotation of generator to improve the commutation. This brush shift will improve the commutation, but it produces an additional demagnetization. This method was used only up to 1910 because more the load, the MNA will fluctuate always. Shifting brushes always is severe pain in the neck. So now by shifting brushes to MNA, commutation will improve, but due to additional demagnetization, terminal voltage will fall. So I have already told you, suppose if you are going to shift the brushes to MNA whenever the load is happening, so here the commutation will improve, but due to additional demagnetization, the net flux decreases, so EG will decreases, so therefore the terminal voltage will also decrease. But even after doing this, there are some effects. There are iron loss increases, maintenance and repair increases, and design cost increases. Even if you shift the brushes to MNA always, the demagnetization will improve and the terminal voltage will follow, and even after that the iron loss will increase and the maintenance and repair will always increase and the design cost increases. So these are the side effects if you shift the brushes to the MNA. So therefore by shifting the brushes to MNA, commutation will improve, but due to additional demagnetization, the terminal voltage will fall because the overall flux is decreased. But even after doing this, there are some effects like their iron loss increases, maintenance and repair increases, and design cost increases. So finally I can say that whenever the load is changing, the MNA changes. So if you shift that brushes to the MNA, always what is going to happen is additional demagnetization is going to get happen. So overall flux decreases, so EG decreases and terminal voltage will decrease. And also the iron loss increases and the maintenance and repair cost increases, so design cost is also increases. So all this is going to happen if you shift the brushes to the MNA. The methods to reduce the armature reaction and its effects. So what are the methods? So we are going to discuss the methods which are going to reduce the armature reaction and its side effects also, which is pole stacking and the pole champering, pole slotting, and the compensating winding. So these are the methods by which we can say we can reduce the armature reaction and also its effects, which are the pole stacking, pole champering, pole slotting, compensating winding. The first two methods, they only reduce the armature reaction. So first two methods are going to reduce only the armature reaction but not its effects. As the remaining two, they reduce the armature reaction and its effects also. So now we can keep the brushes at the GNA only because now the MNA and GNA are going to always coincide. So now we don't have to shift the brushes to MNA always because you have to keep the brushes always on the GNA itself because MNA is going to coincide with the GNA if you follow these methods. The methods to reduce armature reaction and its effects are the pole stacking, pole champering, pole slotting, compensating winding. The first two methods can only reduce armature reaction, whereas the last two methods, they reduce armature reaction and its effects also. So now always the MNA and GNA are going to coincide always, so therefore you don't have to shift the brushes at any load condition. So this is the beautiness of these methods. The methods to reduce armature reaction and its effects are the pole stacking, pole champering, pole slotting, compensating winding. The first two methods are going to reduce only the armature reaction, whereas the last two methods, they reduce the armature reaction and also its side effects. So now we can keep the brushes at the GNA always. Compensating winding is placed on the pole shoe. So compensating winding is placed on the pole shoe, connected in series with the armature through brushes for the automatic cancellation or neutralization of the armature flux under the pole. So compensating winding is placed on the pole shoe, connected in series with the armature through brushes for the automatic cancellation or neutralization of the armature flux under the pole. So armature ampere turns is equal to clockwise ampere turns, which is equal to armature ampere turns is equal to clockwise ampere turns, which is equal to IA by A into Z by 2 is equal to IA into ZC by 2. So ZC is equal to Z by A. So therefore ZC is equal to total compensating conductors, and ZC dash is equal to ZC by B, which is total compensating conductors per pole. So ZC dash is equal to ZC by B is equal to total compensating conductors per pole, which is equal to ZA by AB. Use when pole arc or pole pitch is not mentioned. You have to use this whenever the pole arc or pole pitch is not mentioned. But now ZC dash is equal to Z by AP into pole arc by pole pitch. So total compensating conductors per pole whenever the pole arc and pole pitch are mentioned. So these are the two formulas that you always have to keep in mind. ZC dash is called as the total compensating conductors per pole. So whenever the pole arc and pole pitch are mentioned, whereas this is the formula if pole arc and pole pitch are not mentioned. So compensating winding means which is placed on the pole shoe, which is connected in series with the armature through brushes for the automatic cancellation of the or neutralization of the armature flux under the pole. So armature ampere turns is equal to clockwise ampere turns. So IA by A into Z by 2 is equal to IA into ZC by 2. So IA cancels, 2 cancels, and ZC is equal to Z by 2 you are going to get here, Z by A. So ZC is equal to Z by A. But ZC is called as the total compensating conductors. ZC is called as the total compensating conductors, and ZC dash is equal to ZC by P, total compensating conductors per pole. And Z by ZC is nothing but Z by A. So Z by A into P used when pole arc and pole pitch is not mentioned, whereas Z by AP into pole arc by pole pitch whenever the pole arc and pole pitch are mentioned, which is total compensating conductors per pole. So armature ampere turns is equal to clockwise ampere turns, which is equal to IA by A into Z by 2, because half of the portion, half of the conductors will have the half of the conductors they are going to cancel with the help of this compensating winding, which is Z by 2, and each winding and each parallel path will have a current of IA by A is equal to IA into just ZC by 2, which is ZC by 2. See, armature ampere turns is equal to clockwise ampere turns. See, half of the conductors will have the half of the conductors are going to have the current of IA by A. So IA by A into Z by 2 is equal to IA into, and here for one turn there are two other conductors. For one turn there are two conductors. So for n turns there are ZC conductors. So with the cross multiplication we are going to get the number of compensating winding turns is equal to ZC by 2. So which is ZC by 2. And the current is passing is called as the armature current, because this is connected in series with the armature ampere turns. So it is connected in series with the armature winding. So current is IA. So if you solve this one, we are going to get ZC is equal to Z by A. ZC is called the total compensating conductors, and ZC dash is equal to ZC by P, which is total compensating conductors per pole. Whereas ZC is equal to Z by A. So Z by A into P used when pole arc and pole pitch is not mentioned, but ZC dash is equal to Z by A P into pole arc by pole pitch, total compensating conductors per pole. So finally I can say that compensating winding is placed on the pole shoe, connected in series with the armature through brushes for the automatic cancellation or neutralization of the armature flux under the pole. Armature ampere turns is equal to clockwise ampere turns. As per not clockwise, this is called as the compensating ampere turns. This compensating winding ampere turns. So armature ampere turns is here in each parallel path the current is IA by A, and the number of we can say the number of turns is equal to Z by 2, because half of the turns will have IA by A, which is Z by 2 is equal to, here the current in the compensating winding is IA into, I have already told you one turn will have two conductors, so number of turns of compensating winding will have ZC conductors. So if you do the simplification, we are going to get ZC by 2. So therefore ZC is equal to Z by A. ZC is called total compensating conductors. So ZC dash is equal to ZC by P, which is total compensating conductors per pole. If ZC is equal to Z by A, so Z by A into P used when pole arc and pole pitch is not mentioned. Otherwise, ZC dash is equal to Z by AP into pole arc by pole pitch. total compensating connectors per pole. So this is the general formula. The total compensating connectors per pole is equal to Z by AP into pole arc by pole pitch. So Z dash is equal to Z by AP into pole arc by pole pitch, which is the total compensating connectors per pole. That is called the total number of armature connectors. A is the number of parallel paths and P is the number of poles. The process of current reversal in the coil when it gets short circuited in the brush is called as the commutation. The time taken to brush move from one segment to other segment is called as the commutation, commutation time Tc. In this period, the coil remains short circuited in current reversal. If the current reverses completely within the commutating time, then commutation is successful. Otherwise, it is delayed commutation or nonlinear commutation, which produce sparking at the trailing edge of the brush. So practically, the coil undergoing commutation contains small inductance property, and due to change in current, there will be voltage induced in it. This is called as the reactance voltage. According to Lenz's law, it will oppose the change in current. It will oppose the change in current or the commutation process and takes place delay and makes it delayed to produce a spark at the end of the commutating time. This repeat for every coil passed by a brush. In order to make the commutation successful, the opposition factor reactance voltage need to be opposed or cancelled. This is the basis function of interpole. Cancel the ER for the coil undergoing the commutation. Then all the problems solved and then everything is happy. So the process of current reversal in the coil when it gets short circuited in the brush is called as the commutation. The time taken to brush move from one segment to other is called as the commutating time Tc. In this period, the coil remains short circuited and the current reversal. If the current reverses completely within the commutating time, then the commutation is successful. Otherwise, it is said to be delayed commutation or nonlinear commutation, which produces sparking at the trailing edge of the brush. So practically, the coil undergoing commutation contains small inductance property, and due to change in current, there will be voltage induced in it. It is called as the reactance voltage. According to Lenz's law, it will oppose the change in current or commutation process and makes it delayed to produce a spark at the end of the commuting time. This repeat for every coil passed by a brush. In order to make the commutation successful, the opposition factor, the reactance voltage need to be opposed or cancelled. This is the basic function of the interpole. It is going to cancel the reactance voltage ER for the coil undergoing the commutation. Then all the problems solved and then everything is happy. So this is the basic function of the interpole. So what is trying to say is that nothing but, say at the commutation, whatever the coil which is going under the commutation, it is going to change its current direction from one direction to other direction. So if this is happened successfully, then the commutation is successful. But practically this won't happen because the coil will have small amount of inductance, so it will never change it will change the opposition of the current. So it will oppose a change in current. So therefore a voltage is going to get induced, which is called the reactance voltage. So whatever the coil which is undergoing the commutation, it will have some reactance voltage. So it will oppose a change in current. So therefore at the end also the current will be the same direction. So therefore a sparking is going to occur at the trailing edge of the brush. So we can say the commutation failure. So if you remove this ER, then everything is happy because the commutation is successful. So we have to remove this ER with the help of the interpole. That is the meaning of this concept. The process of current reversal in the coil, which is when it gets short circuited in the brush, is called as the commutation. The time taken to brush move from one segment to other is called as the commutating time Tc. In this period, the coils remain short circuited and the current reversal must happen. So in this, the commutation time, the coil is short circuited and the current direction should change in this time only. If it is not happen, then definitely we can say commutation is failure. If it happens in this Tc, in this commutation time, the coil is short circuited and the current should change only in this time. If it happens, then the commutation is successful. If it does not happens, then we can say it is said to be commutation failure. So if the current reverses completely within the commutating time, then commutation is successful. Otherwise, it is a delayed commutation or nonlinear commutation, which means commutation is failure. So which produces the sparking at the trailing edge of the brush. So practically the coil undergoing the commutation contains small inductance property, and due to change in current, there will be voltage induced in it, which is called as the reactance voltage. And according to Lenz's law, it will oppose a change in current or commutating process and makes it delayed to produce spark at the end of commuting time. This repeats for every coil which is passes through a brush. So in order to make the combustion successful, the opposition factor reactance voltage need to be opposed or cancelled. This is the basic function of interpole. It will cancel the ER for the coil undergoing the combustion, then all the problems solved, and then everything is happier. So we can say that finally the process of current reversal in the coil, when it gets short circuited in the brush, is called as a commutation. So the time taken to brush move from one segment to other segment is called as the commuting time. So in this period, the coil remains short circuited and the current reversal. If the current reverses completely within the commuting time, then commutation is successful. Otherwise, it is said to be a delayed commutation or the non-linear commutation, so which produces sparking at the trailing end of the brush. Practically, the coil undergoing commutation contains small inductance property, and due to change in current, there will be a voltage induced in it, which is called as the reactance voltage ER. According to Lenz's law, it will oppose the change in current or combustion process and makes it delayed to produce spark at the end of the commuting time. This repeats for every coil which passes by a brush. In order to make the combustion successful, the opposition factor reactance voltage need to be opposed or cancelled. This is the basic function of interpole. It cancels the reactance voltage ER for the coil undergoing the commutation, then all the problems solved, and then everything is happier. So in the combustion time itself, the current should reverse its direction and the coil is under short circuited. If it happens in a time TC, it is called the combustion successful. Otherwise, it is said to be a combustion failure. So basically, combustion failure happens because when there is a change in current, the coil will have inductance. So reactance voltage is going to get engaged. So therefore, it will oppose the commutator. So a combustion failure will happen. So current will never completely change its direction. So therefore, because of this combustion failure happens, a spark is going to get occur. So therefore, we have to remove this ER. With the help of interpole, we are going to remove this ER. So finally, I can say that the process of current reversal in the coil when it gets short circuited in the brush is called as commutation. The time taken to brush move from one commutator segment to other commutator segment is called the commuting time TC. In this period, the coils remain short circuited in current reversal. If the current reverses completely within the commuting time, then combustion is successful. Otherwise, it is said to be delayed commutation or nonlinear commutation, which produces sparking at the trailing edge of the brush. Practically, the coil undergoing combustion contains small inductance property, and due to change in current, there will be voltage induced in it. This is called the reactance voltage. According to Lenz's law, it will oppose the change in current or commutation process and makes it delayed to produce spark at the end of the commuting time. This repeats for every coil which passes by a brush. In order to make the combustion successful, the opposition factor, reactance voltage, need to be opposed or cancelled. This is the basic function of interpole. So cancelling the ER for the coil undergoing commutation, then all the problems solved, and then everything is happier. Methods to improve commutation are resistance commutation, EMF or voltage commutation. So these are the two methods to improve the commutation. One is called as the resistance commutation and the EMF or voltage commutation. So these are the two methods. The methods to improve the commutation are the resistance commutation, EMF or voltage commutation. The methods to improve the commutation are the resistance commutation or the EMF or voltage commutation. The methods to improve the commutation process are the resistance commutation or the voltage or EMF commutation. Conductivity of different materials is as follows. For different types of conductivity of materials. Copper has more conductivity than carbon. Carbon has more conductivity than the electrographite. And electrographite has more conductivity than the carbon graphite. And the carbon graphite has more conductivity than the copper graphite. So these are the different types of conductivity of different materials. Copper has more conductivity than carbon. Carbon has more conductivity than electrographite. And electrographite has more conductivity than carbon graphite, and a carbon graphite has more conductivity than copper graphite. So copper has more conductivity than carbon, carbon has more conductivity than electrographite, electrographite has more conductivity than carbon graphite, and the carbon graphite has more conductivity than copper graphite. So copper has more conductivity than carbon, carbon has more conductivity than electrographite, electrographite has more conductivity than carbon graphite, and carbon graphite has more conductivity than copper graphite. Resistance commutation, we must use high resistance brush, so no spark. So in resistance commutation, we must use high resistance brush, so no spark. So presently we use the carbon graphite. So presently we use the carbon graphite for brushes, and for low voltage, high current applications, we use the copper graphite. So I already told you the two methods which are going to improve the commutation are the resistance commutation and the EMF or voltage commutation. So in resistance commutation, we must use the high resistance brushes, so no spark is going to get occur. I already told you out of this, the copper graphite has a less conductivity, so more resistivity. Then the second one is the carbon graphite. But practically we prefer the carbon graphite, but for low voltage and high current applications we use the copper graphite. So in resistance compression we must use the high resistance brushes, so no spark. Presently we use the carbon graphite for making the brushes, and for low voltage high current applications we use the copper graphite. But for the remaining for the small applications we use the carbon graphite for making the brushes. For low voltage and high current applications we use the copper graphite. Poles are commutating poles are small poles compared to main poles located in the interpolar region. I have already told you, interpoles are the commutating poles are small poles compared to main poles located in the interpolar region, midway between the main poles. These are also electromagnets with interpole winding connected in series with the armature through brushes in order to have automatic neutralization of the interpolar zone. And they have two functions: to produce the counter flux on the coil undergoing compression in order to cancel the reactance voltage, to reduce the cross magnetization under the pole tips, top or bottom of the pole. In order to achieve these two functions successfully, interpole polarity should be equal to the polarity of the main pole head of generator rotation. So interpoles are commutating poles. So interpoles are commutating poles are small poles compared to main poles located in interpolar region, midway between the main poles. These are also electromagnets with interpole winding connected in series with the armature to brushes in order to have the automatic neutralization of the interpole zone, and they have two functions: to produce the counterflux on the coil undergoing compression in order to cancel the reactance voltage, to reduce the cross magnetization under the pole tips or top or bottom of the pole. In order to achieve these two functions successfully, interpole polarity should be equal to the polarity of main pole head of generator rotation. So interpoles are commutating poles are small poles compared to main poles located in interpole region midway between the main poles. These are also electromagnets with interpole winding. So therefore these are also electromagnets with interpole winding connected in series with the armature through brushes in order to have the automatic neutralization of interpole zone. So they have two functions: to produce the counterflux on the coil undergoing compression in order to cancel the reactance voltage, to reduce the cross magnetization under the pole tips or top or bottom of the pole. In order to achieve these two functions successfully, interpole polarity should be equal to the polarity of the main pole head of generator rotation. All this concept I have already told you. So basically interpoles are commutating poles. Interpoles are also called as the commutating poles. They are basically small poles compared to main poles located in interpolar region, midway between the poles. These are also electromagnets with interpole winding connected in series with the armature through brushes in order to have automatic neutralization of the interpole zone. They have two functions: to produce the counter flux on the coil undergoing compression in order to cancel the reactance voltage, to reduce the cross magnetization under the pole tips top and bottom or bottom of the pole. In order to achieve these two functions successfully, interpolar polarity should be equal to the polarity of the main pole head of generator rotation. So this interpoles have two functions: to reduce the reactance voltage and also to produce the flux which is going to reduce the cross magnetization. Tapered in shape with more interpolar air gap not to get saturated easily as the load current flow in the interpolar winding. So I have already told you these interpoles are tapered in shape. They are basically tapered in shape with more interpolar axis, with more interpolar air gap not to get saturated easily as load current flow in the interpolar winding. So as the load current is going to flow through this interpolar winding because armature winding and interpolar winding are connected in series. So they are basically tapered in shape, and the more air gap is required, so therefore they should not get saturated easily because load current is going to flow through this interpolar winding. So these interpoles are tapered in shape with more interpolar air gap between the interpoles and the armature. They have a huge amount of air gap, so not to get saturated easily as load current is flowing through the interpolar winding. So more air gap means it will never become saturated easily. By placing interpoles, now we can no need to move brushes from GNA. So I have already told you, if you keep the interpoles, now always GNA and MNA are going to coincide each other. So now you don't have to shift your brushes from GNA. because MN is always in the GNA axis only. So now no need of shifting the brush even if the load is changing. So by placing the interpoles now we can no need to move the brushes from GNA. So I have already told this important point. So interpoles or commuting poles are small poles compared to main poles located in interpolar region midway between the main poles. These are also electromagnets with interpolar winding pattern in series with armature through brushes in order to have the automatic neutralization of the interpole zone. They have two functions. First one is that to produce the counter flux on the coil undergoing compression in order to reduce the reactance voltage. To reduce the cross magnetization under the pole tips, top or bottom of the pole, in order to achieve these two functions successfully, interpole polarity should be equal to the polarity of the main pole head of generator's rotation. And these interpoles are tapered in shape with more interpolar air gap, not to get saturated easily as load current is flowing in the interpole winding. By placing the interpoles, now we can no need to move the brushes from GNA. Compensating winding is used for neutralizing the armature reaction, and the interpole winding is used for improving the commutation. It's a very important point. This compensating winding is used for neutralizing the armature reaction, and interpole winding is used for improving the commutation. So this is a very important point. This compensating winding is used for neutralizing the armature reaction, and the interpole winding is used for improving the commutation. So compensating winding is used for neutralizing the armature reaction, whereas the interpole winding is used for improving the commutation process. So this is a very important point. So always compensating winding is used for neutralizing the armature reaction, and whereas the interpole winding is used for improving the commutation process. So always we can say that the compensating winding is used for neutralizing the armature reaction, whereas the interpole winding is used for improving the commutation. These things I have already told you in the class itself. So no load characteristics. So no load characteristics means is a graph between the EMF with the no load induced EMF versus the field current. So no load characteristics or open circuit characteristics means it is a graph between the EMF induced versus the field current. And the load characteristics means internal characteristics and the external characteristics. Internal characteristics means a graph between the EMF generated and the armature current. And the external characteristics means the graph between the terminal voltage and the terminal current IA. So therefore IA is nearly equal to load current. So no load characteristics means the graph between the no load EMF generated with respect to field current. And the load characteristics of two types, internal characteristics and external characteristics. Internal characteristics means the graph between the EMF generated and the armature current. External characteristics means the graph between the terminal voltage and the terminal current. And terminal current is nearly equal to the armature current. So in DC series generator is used in power plants as excitation. So DC series generator is used in power plants for excitation as excitation systems. In wall Reynolds speed control, ships, aircrafts. So this DC series generator is basically used in power plants as excitation systems, in wall Reynolds speed controls, and the ships, and also in the aircrafts. So these are some of the applications there we are going to use the DC series generator. So DC series generator is used in power plants as excitation systems. So for producing the field current of the motor winding, for the field winding, to produce the field current in the field winding of power plants, the synchronous machines. And also in the wall Reynolds speed control also we are going to use this DC series generator. And also the ships also we are going to use, and also in the aircrafts also we are going to use here. Whereas the DC shunt generator is used in the battery charging, because DC shunt generator, the terminal voltage from no load to full load is very less amount of change. So for charging of battery we need a constant supply. So there we are going to use this DC shunt generator is used in battery charging and small DC power supplies also. So DC shunt generator is used in battery charging and small DC power supplies. DC series generator rising characteristics is used for boosters, and dropping characteristics is used for arc welding. So in DC series generator, the rising characteristics is used for booster purpose, and dropping characteristics is used for arc welding. So in DC series generator, the rising characteristics is used for boosters, and the dropping characteristics is used for arc welding. So we can say DC series generator can be used for two applications. The rising characteristics is used for boosters, and the dropping characteristics is used for arc welding. So in a DC series generator, the rising characteristics are used for the boosters, and the dropping characteristics are used for the arc welding purposes. Cumulative compound generator is used in large rating DC power supplies and also widely manufactured by using however we can make like others. I have already told you. So cumulative compound generator is used in large rating DC power supplies and also widely manufactured because by using diverter we can make like others. So if you keep the diverter, we can make the cumulative compound generator to any other machine that we want. We can make DC series motor, DC shunt motor with the help of diverter. So cumulative compound generator is used in large rating DC power supplies and also widely manufactured because by using diverter we can make like others. So cumulative compound generator is used in large rating DC power supplies and also widely manufactured, and by using diverter we can make like others. In welding, we need low voltage and high current. So DC series generator and differential DC generator both used for arc welding, but differential is best in arc welding and the differential compound generators are not used for regular power supplies. I already told you in welding, see in series this generator it has two characteristics. One is the rising characteristics is used for boosting and the dropping characteristics for arc welding. So in welding, we need low voltage and high current. So DC series generator and differential DC generator both are used for arc welding, but differential is best in arc welding when compared to series this generator. So differential compound generators are not used for regular power supplies. So therefore simply we can say for welding we can use both things, DC series generator or DC differential generator, but we prefer DC differential generator rather than the DC series motor. So in welding we need low voltage and high current. So series DC generator and differential DC generator both are used for arc welding, but differential is based in arc welding and differential compound generator are not used for regular power supplies. So percentage of voltage regulation is equal to no load voltage minus terminal voltage by no load voltage into 100. So this is the formula for all rotating machines, but for transformer it is different, which is E2 minus V2 by E2. These things I have already told you. But for rotating machines which is opposite, E2 minus V2 by V2 here. So E0 minus V by V into 100. Just replace here E2 by V. So E0 is called as the no load voltage of generator. V is called the rated terminal voltage of generator at rated load. So percentage of voltage regulation is equal to E0 minus V by V into 100, where E0 is called as the no load voltage of generator and V is called as the rated terminal voltage of generator at a rated load. So for generator, we figure out the voltage regulation, and for motor, we figure out the speed regulation. So for generator, we figure out the voltage regulation, and for motor, we try to figure out the speed regulation. So therefore, the percentage of voltage regulation is equal to E0 minus V by V into 100. E0 is called as the no load voltage of generator, and V is called as the rated terminal voltage of generator at rated load. Always V is less than E0. See, plant compound have least percentage voltage regulation, so it is the best one. So flat compound have the least percentage voltage regulation out of all the generators. The flat compound generator has the least compound voltage regulation, so it is the best. So less voltage regulation means less voltage drop, so therefore it is best. So therefore we can say less voltage regulation means less voltage drop because the internal impedance, so it is the best one. So therefore the flat compound DC generator has the least percentage voltage regulation, so it is the best one. The rating of generator is always a terminal voltage P at rated load, and always E0 is greater than V, always. The rating of generator is always a terminal voltage P at rated load. E0 is always greater than V, always. See, whatever the rating that you see on a generator is always a terminal voltage at rated load. So whatever the rating of a generator which is given on the nameplate details is always a terminal voltage at a rated load, and E0 is always greater than V, which is no load voltage of generator is always greater than the rated terminal voltage. So the rating of generator which you see on the nameplate ratings of generator, it is always a terminal voltage at the rated load, and E0 is always greater than V, which is always the case. The rating of generator is always a terminal voltage V at rated load, which is E0 is always greater than V, always. A synchronous machine has its field winding on the stator and the armature winding on the rotor. When running under steady conditions, its air gap field is stationary with respect to stator. A synchronous machine has its field winding on the stator and the armature winding on the rotor. When running under steady conditions, its air gap field is stationary with respect to stator. See, I already told you, you can say that a synchronous machine has its field winding on the stator and armature winding on the rotor. So when running under steady conditions, its air gap field is stationary with respect to stator. So I have already told you, for low rating machines we keep the field winding on the stator and the armature winding on the rotor. But for higher rating applications, we keep the armature winding on the rotor, on the stator, and the field winding on the rotor. So for low rating machines, we keep the field winding on the stator, armature winding on the rotor. But for higher rating machines, we keep the armature winding on the stator and the field winding on the rotor. So universally, all generators are conducted in parallel. So these things I have already told you in the previous classes only. Universally, all the generators are conducted in parallel. So because of many generators conducted in parallel, if any one generator generates more or less voltage, still the bus bar voltage is always constant because of so many others generates. See, we can say that, so universally all the generators are going to conduct in parallel. Suppose if one generator is generating more than that particular rated voltage, then still the voltage will be same constant because the remaining generators are generating at that voltage only. So bus bar voltage is always constant if any one generator generates more voltage or less voltage than the bus bar voltage. So we can say that universally all generators are conducted in parallel. So because of many generators conducted in parallel, if any one generator generates more or less voltage, still the bus bar voltage is always constant because of so many other generators. So always design machine at the rated load and they will give the maximum efficiency. So always design the machine at rated load and then they give the maximum efficiency. So always design the machine at the rated load and then they will give the maximum efficiency. So according to the demand, add or remove generators from parallel. Suppose if the demand is increasing, then add the generators in parallel. Suppose if the load demand is decreasing, then just remove the generators from parallel. So if more is the demand, just give more is the supply by more generators. If the demand is less, then give less number of generators. So the condition for connecting generators in parallel are voltage and polarity. See, the compulsory conditions for connecting the generators in parallel, they should have the same amount of voltage generation and the polarity of the connection is also same. So these are the two conditions that must be compulsory met before connecting the generators in parallel. So these are some of the important points. Universally, all generators are connected in parallel. So because of many generators connected in parallel, if any one generator generates more or less voltage, still the bus bar voltage is always constant because of so many others are going to get generates. So always design the machine at rated load and they give the maximum efficiency. According to the demand, add or remove generators from the parallel. And the compulsory condition for connecting generators in parallel or voltage and polarity should be always same. Desirable characteristics. The desirable characteristics, without them also we can orbit in parallel. They are. See, these are called as the desirable characteristics. These are called as desirable characteristics. Means these are not necessary characteristics. Without them also we can operate in parallel. Without these conditions also we can still connect the generators in parallel. These are, now we will discuss what is these characteristics. So, grouping characteristics, prime movers, voltage regulation should be same. So therefore, the grouping characteristics, the prime movers and the voltage regulation should be same. So the grouping characteristics for the prime movers and the grouping characteristics for the voltage regulation should be same. And the load sharing happens according to the ratings. The load sharing happens according to the ratings. More is the rating, more is the amount of load shared. If the generator taking more load means its mechanical input must be increased. See, if you increase the mechanical input only, the generator is giving more amount of output, electrical output. So if the generator is taking more load means its mechanical input is increased. If the generator is taking less load means its mechanical input must be decreased. So we can say more is the mechanical input, more is the output load it can take. So less is the mechanical input, less is the output it can take. So for stable operation, voltage grouping characteristics must be same. So for stable operation, voltage grouping characteristics is must same. So therefore we can say the desirable characteristics, and without them also we can operate the generators in parallel. They are grouping characteristics for the prime mover and the voltage regulation should be always same. And the load sharing happens according to the ratings. More is the rating, more the load can share. If the generator is taking more load means its mechanical input must be increased. So more is the mechanical input, more is the electrical output it can take. And if the generator is taking less load means its mechanical input must be decreased. So therefore simply we can say that, so less the mechanical input means less the electrical output it can take. So for stable operation, voltage dropping characteristics is must be same. For stable operation, voltage dropping characteristics is must. So for stable operation, voltage dropping characteristics is must. So there is a drooping characteristics, then only we can say the stable operation is going to get occur. So for stable operation, voltage drooping characteristics is must and compulsory. So these are the desirable characteristics, means we can say these are not necessary characteristics, but still without them also we can operate the generators in parallel. The two necessary conditions are the voltage should be same and the polarity of the connection is also same. So these are the only two necessary conditions, and remaining everything is called as the desirable characteristics. These generators have rising characteristics, so now parallel operation is not possible. I've already told you series generator has two types of characteristics. One is called as the rising characteristics and dropping characteristics. So rising characteristic means it can be used as a booster, and dropping characteristics means it can be used as a for arc welding purposes. So we can say as it has the rising characteristics, so it is never used for parallel operation. So that is the reason DC series generators having the rising characteristics. So now parallel operation is not possible. So parallel operation is possible only if they have the drooping characteristics. So whenever the load increases, the terminal voltage should decrease. It is called as a drooping characteristics. So this is not possible in a series generator. So simply we can say that it is said to be parallel operation is not at all possible. This DC series generator has rising characteristics. So now parallel operation is not possible. Whereas DC shunt and DC shunt generator and DC under compound generators used for parallel operation, but between two shunt is best. I have already told you the under compound is going to lie. It is going to lie between the shunt and the. I have already told you DC shunt generator and DC under compound generator used for parallel operations, but between them between two the shunt is the best one because it has the less amount of voltage regulation. So we can say that simply that if we compare the DC shunt generator and the DC under compound generator, between them both has the voltage drooping characteristics. I have already shown the graphs for the voltage, terminal voltage and terminal load current. I have already shown the graph. They basically have the voltage drooping characteristics. But now between them the DC shunt generator is the very best one. So this is a very important point. If you are going to compare the DC shunt generator and the DC under compound generator, both have the voltage drooping characteristics. So both are used, but out of them DC shunt generator is the best one. The machine with low drooping characteristics shares more load. So this is a very important point. See, the less amount of drooping means it can share more amount of load. These things also I have already told you. So less is the drooping means it can share more amount of load. The machine with low drooping shares more amount of load because the frequency should be same. So frequency should be always constant, so therefore it can share the more amount of load. So therefore the machine with low drooping shares the more load. By using equalizer rings, we can make series machine to operate in parallel. Same method is used for over compound machines also. See, I already told you DC series machines and the DC series generator and the DC over compound generators both have the rising characteristics. So then we can say that they are not used for parallel operation. But if you want to use them, still we can use them by adding an extra which is called as the equalizer ring. So by adding an equalizer ring, yes, we can make this DC series generator and the DC over compound generator for parallel operation. So by adding the equalizer rings, we can make the DC series generators and the DC over compound machines to operate in parallel. So if we add it, because the DC series generator and the DC over compound generators have the rising characteristics, so they are never used for parallel operation, but still we can use them if we add an extra equalizer rings. So by using equalizer rings, we can make DC series generator and the DC over compound generator to operate in a parallel. So by using equalizer rings, we can make series machines to operate in parallel. Same method is also used for the over compound machines. And ore must also have drooping characteristics. As load increases, speed must decrease. So governor opens to increase the speed to the required level, and this is the compulsory condition. So prime mover should also have the grouping characteristics. So prime mover should also have the grouping characteristics, means whenever the load increases, the speed of the rotor will decrease. So governor opens to increase the speed to the required level, and this is the compulsory condition. I have already told you, suppose if the load demand increases, thus the speed of the synchronous machine, the rotor will decrease. Then the governor is going to get open its value, so incoming steam value will increase. So therefore, again the speed will increase to the required level. So this governor characteristics should also have the grouping characteristics. So we can say the prime mover must also have the grouping characteristics. As the load increases, the speed decreases. So governor opens to increase the steam inflow, so therefore the speed to the required level, and is the compulsory condition. So prime mover must also have the grouping characteristics. As the load increases, speed decreases. So governor opens to increase the speed to the required level, and this is the compulsory condition. Energy cannot be created, it can only convert. See, we cannot create the energy, we can only convert from one form to another form. So energy we can't create it or we can't destroy it, only we can transfer from one form to other form. So for this generator, I already told you we have to use the Fleming right hand rule, because in the generator there is the R here, so we have to use the right hand thumb rule. I already told you the thumb is going to represent the moment or force or torque, whereas the forefinger is going to represent the flux direction, and the middle finger is going to show the direction of the EMF or current. In a generator, we know the value, we know the direction of the flux, we know the direction of the mechanical torque, but we don't know what is the direction of the EMF or the current induced in the wires. This we can know, we can figure out with the help of this Fleming right hand rule. So these two are known quantities, and this is the unknown quantity. Here, whatever this thumb is called as the mechanical torque, this is basically a mechanical torque direction. For DC motor, we use the Fleming left hand rule. So for same configuration, the thumb is going to show the moment or force or torque, and the forefinger is going to show the flux, and the middle finger is going to show the EMF or current. So in a DC motor, the flux direction and the EMF or current direction we know. This is a known quantity, but we have to know what is the direction of the torque or force or movement, which is called as the unknown quantity. So this direction we can figure with the help of this Fleming left hand rule. So always whatever the torque here, it is called as the electrical torque. It is always the electrical torque. So if you want to use the general formula, then you have to use this one, which is F cap is equal to I cap cross V cap. Here F cap is nothing but it is always electrical torque. So this is always an electrical torque. So in the generator, the mechanical torque is always opposite to electrical torque. So this is the thing that you always have. This is called as electrical torque. Whereas in motor it is also electrical torque. But this is called as a mechanical torque. This is always a mechanical torque. But you have to choose electrical torque, which is opposite to the mechanical torque. So this is nothing but here F is always called as the electrical torque. It is always the electrical torque. For motor this is electrical torque, but here for generator it is a mechanical torque. So we have to use the opposite direction. It is called as the electrical torque. So this is the thing that you always. So you can apply this basic formula for both DC generator and also for the DC motor. But you have to only thing which is keep in mind, here F is called as electrical torque always is the direction of the electrical torque. In the generator, the electrical torque and mechanical torque are opposite in direction. This is a very important point that you always need to keep in mind. So just by changing supply voltage polarity, we can change the direction of rotation of DC motor. So just by changing the supply voltage polarity, we can change the direction of rotation of DC motor. So these things I have already told you. So if you change the supply voltage, if you change the polarity of the supply voltage, definitely we are going to change the direction of the current. So we can change the direction of the DC motor. So in a DC motor, F is equal to B into I into L. So this is the force experienced by a conductor of length L is the carrying current of I in a magnetic field B. And also torque is directly proportional to flux into armature current. See, I is equal to positive and negative. We can make motor in any direction. So if you change the IA from positive to negative, then definitely we are going to change the current direction also. And the flux is equal to positive negative, we can make motor in any direction, either by changing flux direction or either by changing the armature current direction. We can change the rotation of the rotation of the direction of the motor. So either by changing flux from positive to negative, we can change the direction of the motor. Similarly, we can change the direction of the motor from positive to negative, if you give a positive to negative armature current also, we can change the direction of the motor. But if both are changed, then the torque is again positive, so it will never change. So always you have to change only one thing, but not both things simultaneously. If you change any one at one time, then only which direction is going to get changed. Otherwise, it will be in the same direction. DC motors have more superior speed control than anything. So DC motors have more superior speed control than anything. So DC series motor has highest starting torque than any other motor in the world, but it has limited applications. So this is a very important point that you always need to keep remember, which is DC motors have the more superior speed control than any motor, and the DC series motor has the highest starting torque than any other motor in the world, but it has the limited applications. So we can say that if you compare DC motors and AC motors, DC motors are more preferred because the speed control method is very good with the DC motors when compared to AC motors. That is the reason DC motors are always preferred when compared to AC motors. Whereas DC motors has the highest starting torque. If you compare any other motor, DC series motors has the highest starting torque, but the applications are very limited. So DC motors have the more superior speed control than any motor, and the DC series motor has the highest starting torque than any other motor in the world, but it has limited applications. So DC motors have more superior speed control than anything, and the DC series motor has the highest starting torque than any other motor in the world, but it has the limited applications. So when a current carrying conductor placed in a field, it experiences a force F is equal to BIL newtons, and its direction is according to the Fleming left-hand rule. See, I have already told you very important point. Suppose if you keep a current carrying conductor, if you place in a field, so if you place a current carrying conductor in a field, magnetic field, it experiences a force FBIL newtons, and its direction is according to the Fleming left-hand rule because it is a motor. Basically, it is a motor. Whenever you place a current carrying conductor in a magnetic field, means it is going to act like a motor. So its direction we can figure out with the help of the Fleming left-hand rule, or simply I have already told you F cap is equal to I cap cross B cap. With the help of that equation also, we can figure out the direction of the torque or force on the conductor. So therefore, I have already told you, whenever a current carrying conductor is placed in a magnetic field, it experiences a force that force magnitude is equal to F is equal to BIL newtons, and its direction is according to Fleming left-hand rule because it is going to act like a motor. So whenever you keep a current carrying conductor in a magnetic field, the torque is going to get exact. It is called as a DC. It is going to act like a motor. So its direction, the moment we can easily figure out with the help of the Fleming left-hand rule, or F cap is equal to I cap cross B cap. The function of commutator in a DC motor is to convert DC to AC and to produce unidirectional torque. It also makes armature flux stationary with respect to main flux, and it is also called as a mechanical inverter. So the function of commutator in a DC motor is to convert DC to AC and to produce unidirectional torque. It also makes armature flux stationary with respect to main flux, and it is also called as a mechanical inverter because in a DC motor, the commutator is going to change the DC supply to AC supply. So it's also called as a mechanical inverter, and because of that we are going to get a unidirectional torque. So it is going to rotate in a unidirectional, and also we can say that it is going to make the armature flux stationary with respect to main flux. So this is the important work of the commutator. The function of a commutator in a DC motor is to convert the AC to DC to AC supply and to produce unidirectional torque, and it also makes armature flux stationary with respect to main flux, and it is also called as a mechanical inverter. DC generator, when it is loaded, current flows. So in a DC generator, when it is loaded, current flows. Therefore, a current carrying conductor is present in a magnetic field, so which experiences a force exactly in the opposite direction to generator rotation. So the prime mover experiences this. The mechanical input should dominate the mechanical opposition, the electrical opposition for energy conversion. So therefore we can say that simply here in a DC generator, when it is loaded, current flows. Therefore, a current carrying conductor is placed in a magnetic field, so which experiences a force exactly in the opposite direction to generator action. So the prime mover experiences this. The mechanical input should dominate the mechanical opposition for energy conversion. I have already told you very important point. See, whenever a DC generator is loaded, the current is going to get flow. So whenever a current carrying conductor is placed in a magnetic field, it experiences an electrical torque, or you can say electrical torque. So this electrical torque direction is opposite to the mechanical torque direction. So this mechanical torque should dominate the electrical torque, then only we can say that the energy conversion is happens, otherwise there is no energy conversion. So this direction you can easily figure out with the help of F cap is equal to I cap cross B cap. I have already told you F cap is equal to I cap cross B cap. With the help of this equation we can easily get F cap is nothing but electrical torque direction. It is always opposite to the mechanical torque direction. So in a DC generator, when it is loaded, when it is loaded, current flows. Therefore, a current carrying conductor is present in a magnetic field, so which experiences a force exactly in the opposite direction to generator rotation. So the prime mover experiences this. The mechanical input should dominate the mechanical opposition for energy conversion. So always you have to remember, whatever the F cap is equal to I cap cross B cap, here the F cap is always going to represent the electrical torque or electrical force. In a DC generator, the electrical torque and the mechanical torque are opposite in direction. So this mechanical torque should dominate the electrical torque. Then only the energy conversion is happening from mechanical to electrical energy. So this is a very important point that you always need to keep in remember. So in a DC motor, EMF is induced according to Faraday's law. Its direction is exactly opposite to supply voltage, which is called as the back EMF or counter EMF. So whatever the back EMF polarity and the voltage supply polarity are opposite of each other. So therefore simply we can say that the current is going to get reduced. So in a DC motor, EMF is induced according to Faraday's law. Its direction is exactly opposite to supply voltage called as the back EMF or the counter EMF. Its polarity is opposite to the supply voltage. So EB is equal to P5 into N by 60 into Z by A. This equation as I have already told you, this is called as a back EMF. So our back EMF, it is the same equation for generating EMF also. These things I have already told you. So therefore the supply voltage should dominate this back EMF, then only the energy conversion is happening from electrical to mechanical in a DC motor. The supply voltage should always dominate the back EMF, then only we can say that the energy is converting from electrical to mechanical in case of the DC motor. So in a DC motor, EMF is induced according to Faraday's law. Its direction is exactly opposite to supply voltage called as the back EMF or counter EMF, and EB is equal to P5 into N by 60 into Z by A. So now we'll discuss types of DC motors. Permanent DC motor, separately excited DC motor, shunt DC motor, series DC motor, and the compound DC motor. Again, the compound DC motor is of two types. One is long shunt and the other one is the short shunt. Long shunt is again cumulative and differential, and the short shunt is also cumulative and differential. So these are the types of DC motors that you are going to see in the nature. So therefore in the electrical course we are going to see the DC motors of permanent DC motors, means the permanent magnets we are going to use there, separately excited DC motors, and the shunt DC motors, series DC motors, and the compound one. Compound one is of two types, compound long shunt, compound short shunt. So again long shunt is again two types. One is called as the cumulative compound and the differential compound, and the short shunt is again which is cumulative compound short shunt and the differential compound short shunt. So these are the type of DC motors which are going to occur in nature. One is called as the permanent DC motors, separately excited, and all these are the self-excited. All these are the self-excited DC motors, which is basically shunt DC motor, series DC motor, and the compound one is of two types, long shunt and short shunt. The long shunt is of two types, one is called as cumulative and other is differential, and the short shunt is again of two types, cumulative and differential. So these are the type of motors that are going to present in the electrical course. Permanent magnet DC motors are used in small fans. See, and the toy motors, some tape recorders in cars for small applications. See, these permanent magnet DC motors are basically used in small fans, toy motors, and some tape recorders, and also in cars for small applications. So this is the use of the permanent magnet DC motors. Means whatever the magnets, they are basically permanent magnet. So whatever the magnets which are used in permanent magnet DC motors are permanent magnet, which are basically used in small fans and toy motors, and some tape recorders, and also in some cars for small applications. So permanent magnet DC motors are used in small fans, toy motors, some tape recorders, and in cars for small applications. DC machines are doubly excited machine, and induction machines are singly excited, and similarly synchronous machine is also doubly excited. So DC machines are doubly excited machine because we are going to give the supply and also we are going to supply the field winding also. So it is called as the doubly excited. So therefore we are going to excite the armature winding, we are going to excite even the field winding. So it is called as a doubly excited machine, because if you see clearly, we are going to excite the armature winding, and also we are going to excite the field winding in case of DC machines and also the synchronous machines. So it is called a doubly excited machine. Whereas the induction machine is a single excited machine, because only on the stator coil we are going to give the excitation, but not on the rotor coil. So this is a very important point that you always need to keep remember. So in the DC machines we are going to excite the armature winding and also the field winding. In the synchronous machines also we are going to give the excitation for the armature coil and also for the field coil. Whereas in induction machines we give excitation to only the stator coil but not to rotor coil. So induction machines are single excited, whereas DC machines and synchronous machines are doubly excited machine. See, under no load in a DC motor, see I have already told you, at no load condition in DC motor, see at no load condition what is going to happen? The current is very less. The current drawn is very less, means EB is nearly equal to V. Then EB into IA is nearly equal to 0. So output power is equal to 0. So whatever the electrical power developed is in the terms of the rotational losses. So whatever the electrical power developed, which is EB into IA is nearly equal to 0. So therefore the output power is equal to 0. So under no load condition in DC motor, the current drawn is nearly 0. So EB is nearly equal to V. So therefore EB into IA is nothing but, here it is nearly equal to 0. So output power is equal to 0. So therefore as load increases, the speed decreases. So EB decreases. So current increases. So torque increases. So in a DC motor, as the load increases, the speed will decrease and the EB will decrease, because EB is directly proportional to N. As N decreases, EB decreases. As EB decreases, then current IA increases, because IA is equal to V minus EB by RA. As EB decreases, IA increases, and torque is directly proportional to armature current. As IA increases, torque increases. To make this speed to the constant one, we will try to increase the speed to the normal case. For DC motor, I have already told you, EB is directly proportional to N into 5, means N is directly proportional to EB by 5, and the torque is directly proportional to flux into armature current. See, as the flux decreases, the speed increases. As the flux decreases, the speed increases and the torque will decrease. You can see clearly from this equation. So whenever the flux decreases, the speed increases and the torque will decrease. So when a DC motor is loaded, it will draw current to develop the torque. So whenever a DC motor is loaded, it will draw a current to develop the torque. Therefore, armature flux coil increases. And affects the main flux called as the armature reaction. It produces two significant effects there. So I have already told you, see, whenever a DC motor is loaded, then we can say simply that whenever DC motor is loaded, it will draw armature current. So it will draw the current. So to develop the torque. Therefore, as the current increases, the armature flux increases. So it is going to affect the main field flux. The interaction of the armature flux and the main field flux is called as the armature reaction. So it will produce the two significant effects. They are demagnetization. So reduction in flux will increase the speed. I have already told you. So because of this, demagnetization is going to occur. It means the resultant flux will decrease. So therefore, as the flux decreases, the speed will increase. It will increase the speed. And the cross magnetization, so distortion of flux will shift the MNA in the opposite direction to rotor rotation and affects the commutation. In order to improve commutation process, brushes need to be shifted in the opposite direction to the motor rotation. It improves commutation but produces additional demagnetization. So but produce additional demagnetization, it will increase the speed while reducing the torque. See, this is a very important point. Already told you very important point. So whenever a DC motor is loaded, it will draw the armature current. So therefore, as armature current is drawn, it is going to produce some torque, and the armature flux will increase, and it is going to affect the main field flux. It is called as armature reaction. It has two significant effects. They are the demagnetization. So there is a reduction in flux, so therefore the speed will increase. Cross magnetization means it is a distortion of flux. So therefore the MNA will shift from GNA in the opposite direction to the motor rotation, and it is going to affect the commutation. In order to improve the commutation, we need to shift the brushes to the opposite direction rotation to the motor rotation. So we have to shift this. Basically, we have to shift these brushes to the MNA. So MNA is quite opposite to the rotation of the motor. So definitely we can say we have to shift the brushes in the opposite direction of the rotation of the motor. So now the commutation is improved. It improves commutation, but it produces additional demagnetization. So again the flux will decrease. So it will increase the speed while reducing the torque, because of this extra demagnetization. So flux decreases means the speed will increase and the torque will decrease. So these are the things that I have already told you. So therefore we can say that whenever a DC motor is loaded, it will draw current to develop the torque. Therefore armature flux coil increases. Armature flux coil increases and it affects the main field flux. It is called as armature reaction. It produces two significant there: demagnetization. So reduction in flux will increase the speed. Cross magnetization means the distortion of flux will shift the MNA in the opposite direction to motor rotation and affects the commutation. In order to improve commutation process, brushes need to be shifted in the opposite direction to the motor rotation. It improves commutation but produces additional demagnetization, which will increase the speed by reducing the torque. So we can say that simply in a DC motor, see, whenever a DC motor is loaded, the current is drawn, the armature current will increase. So then what is going to happen whenever the armature current increases, the armature flux increases. So there is an interaction of the main field flux and the armature flux. It is called as the armature reaction. So because of this, there are two significant effects. One is called the demagnetization. So resultant flux decreases. So therefore speed will increase. And the other one is called the cross magnetization. Cross magnetization means it is a distortion of flux. So therefore MNA will shift in the opposite direction to the motor rotation. So we have to shift the brushes to the, so then the commutation is going to get failure. So if you want to improve the commutation, just you have to shift the brushes to the MNA. So you have to shift the brushes in the opposite direction of the motor rotation. So therefore now the commutation is improved. But even though commutation is improved, there is still demagnetization. So because of that, the flux will further decrease and the flux will further decrease. So therefore the speed will increase and the torque will decrease. So this is the beautiness of this one. As I already told you, the leading pole tip in the motor gets magnetically saturated. So these things I have already told you in the case itself in the motor. So in the motor we are going to try to move in the anti-clockwise direction. I have already told you, easy to remember is AM. AM means anti-clockwise for motor. The leading pole tips in the motor gets magnetically saturated and the polarity of the interpole should be equal to the polarity of the main pole behind the motor rotation. These things I have already told you. The leading pole tips in the motor gets magnetically saturated. The polarity of the interpole should be equal to the polarity of the main pole behind the motor rotation. These things I have already told you in the diagram itself. So the leading pole tips in the motor gets magnetically saturated. The polarity of interpole should be equal to the polarity of the main pole behind the motor rotation. So this is the very important point that you always need to keep in mind. For every DC motor we will figure out. So for every DC motor we are going to figure out the graphs of torque versus armature current, speed versus armature current, and the speed versus torque. So these three graphs we are going to figure out for each and every motor: torque versus armature current, speed versus armature current, speed versus torque. So based on this we will decide this motor is used for which applications. So for each and every motor we are going to draw the graph between the torque versus armature current, speed versus armature current, and the speed versus torque. So for each and every motor we are going to draw these diagrams, and based on this we will see this motor is used for which applications. I have already shown each and every graph of DC motors. Each and every graph I have already shown for each and every motor. The applications of DC shunt motor is same as the induction motor. It is used in steel rolling, aluminium rolling, textiles, spinning wheels, industries, some fans, and centrifugal pumps, etc. Because shunt motor from no load to full load, its speed is almost constant. Even the induction machine from no load to full load, its speed is NR, which is less than NS, and it is quite constant. It is quietly constant. So therefore, simply we can say that the applications of DC shunt motor is same as the DC like AC induction motor. It is used in basically steel rollings, aluminium rollings, textiles, spinning wheels, industries, some fans, and centrifugal pumps. Because there we need the constant speed application, then we are going to prefer the DC shunt motor. So from no load to full load, the speed is almost constant. So we can say that simply there we are going to use, wherever the applications we need constant speed, there we are going to use the DC shunt motor and the induction motor. So the applications of DC shunt motor is same as the single phase induction motor, which is used in the steel rolling, aluminium rolling, textiles, spin weaving industries, some fans, and centrifugal pumps, etc. I have already told you For generator, we are going to figure out the voltage regulation, and for motor, we are going to figure out the speed regulation. So therefore, the percentage of speed regulation is equal to no load speed minus full load speed by full load speed into 100. I've already told you the basic formula, which is E2 minus V2 by E2 for only static machines, whereas E2 minus V2 by V2 for the rotating machines. So similarly, same concept we have to use for even the rotating machines for the speed regulation, which is no load speed minus full load speed by full load speed. So this is a very important formula that you always need to keep remember, which is same as the voltage regulation formula for the rotating machine, which is E2 minus V2 by V2. E2 is nothing but into the no load induced voltage, and V2 is the rated terminal voltage. And so like this we have to use. So the percentage of speed regulation is equal to no load voltage minus the no load speed minus full load speed by full load speed into 100. So NL means no load speed minus full load speed by full load speed into 100. So DC motors have high starting torque than any other motor available. I have already told you DC series motor has the highest starting torque than any other motor, and the DC motors has the excellent speed control characteristics than any other motor. All these things I have already told you. So during no load, for the during no load application of this series motor, what is going to happen? I have already told you EB is directly proportional to flux into speed. As at no load condition, the current IA is nearly equal to 0. So therefore, the flux is nearly equal to 0. But here B is equal to EB. See, as IA is nearly equal to 0 and phi is also nearly equal to, because phi is directly proportional to IA in this series motor. So flux is also nearly equal to 0. But you can see therefore we can say that B is nearly equal to EB because there is no voltage drop. So V is nearly equal to EB. As you can see clearly, N is directly proportional to EB by phi. So V by phi. See, as phi is very less and V is very large, so the ratio is again large. So therefore the speed is very high. So these are used in electric traction, trams, trolleys, cranes and hoists. That is the reason as no load the speed is very high. That is the reason you shouldn't apply at no load condition. Always you have to connect a load and then you have to apply this one. So always you don't have to apply any. See, always you have to operate the DC series motor at load condition, otherwise the speed will be very high. So we can say that simply. So therefore simply we can say that at no load condition the speed is very high. So never operate the DC series motor at no load condition. So during no load, EB is directly proportional to phi into N. IA is nearly equal to 0. So flux is nearly equal to 0 and V is nearly equal to EB. So speed increases. So always at no load the speed is very high. So you don't have to operate you always have to keep a load and then you have to operate the DC series motor. Otherwise speed is very dangerous. It may affect the system also. So never operate the DC series motor at no load condition. So therefore these are used in the electric traction, trams, trolleys and cranes and hoists, because there always load is connected. So always you have to connect the DC series motor whenever there is always a load here. In electric traction, trams, trolleys, cranes and hoists, always load is present. So there we need to use this DC series motor, because there we need there the load is always present and we need the high starting torque. Then we prefer the DC series motor. See, as load increases, then what is going to happen? As the load increases, the IA increases, then phi SC increases. As phi SC increases, then definitely speed will decrease. So therefore, whenever the load increases, the IA increases, so phi SC increases, so speed will decrease. For this DC series motor, I have already shown you the graph is a rectangular hyperbola. That the speed with respect to armature current, I have already told you it is a rectangular hyperbola for a DC series motor. So minimum 15 to 20% load is required initially always. I have already told you, you always have to keep the load. Minimum 15 to 20% load is required initially always. So never operate the DC series motor at no load condition. Always you have to keep a load. The minimum load which is always required is 15 to 20% load is required initially always. Initially you need to keep always a minimum 15 to 20% load. Otherwise the speed is very high, so it will become damage. So these are some of the important points regarding the DC series motor. Now we will see the cumulative compound motor, which is torque is directly proportional to net flux into armature current. In a cumulative compound, the resultant flux is shunt flux plus series flux. So during the no load condition, phi SC is nearly equal to 0 because the current in the series field winding is nearly equal to 0. So phi SC is nearly equal to 0. So it acts better than a shunt but lesser than the series. So it is going to act better than a shunt but less than a series. So therefore the graph is going to lie between the shunt and the series. So it is going to basically act in between these characteristics are going to lie between the shunt and the series. So these characteristics are going to lie between the shunt and the series. It is going to act better than shunt but lesser than series. So then IA increases. As IA increases means as load increases, IA increases. So torque increases. So therefore we can say that as the load increases, then IA increases. So therefore the torque increases. So I have already told you speed is directly proportional to EB by phi. It is directly proportional to EB is nothing but V minus IA into RA plus RSC by the net flux is phi SH plus phi SC. See, as load increases, I have already told you as load increases, then IA increases, then definitely phi SC increases. So as phi SC increases, you can see clearly this denominator is higher than the numerator, so speed will decrease. So therefore, it is better than series but lesser than shunt. So we can say that simply it is better than series but lesser than shunt. So this graph is always going to lie between the shunt and the series. So therefore simply we can say that it is better than series but lesser than shunt. So it is the graph that we are going to get finally. So therefore simply we can say this graph is going to lie between the shunt and the series. This is a very important point that you always need to keep in mind. It is N is directly proportional to EB by phi. It is directly proportional to V minus IA into RA plus RSC by phi SH plus phi SC. As the load increases, IA increases, so phi SC increases, so speed will decrease. So therefore, its characteristics is going to lie between the shunt and the series. So its characteristics is better than series but lesser than the shunt. Cumulative compound DC motor is used in high torque intermittent load cycles like shear metal punches, presses, crushers, some elevators, lifts, conveyors. But for these applications, induction is superior than the cumulative. So therefore, we can say that here in this type of applications that we prefer the induction rather than the cumulative. So cumulative compound DC motor is used in the high torque intermittent load cycles, means sudden loads. Whenever there is a sudden change in load, there we are going to use this cumulative compound DC motor is used in high torque intermittent load cycles like shears, metal punches, presses, crushers, some elevators, lifts, conveyors. But for these applications, induction is superior than the cumulative. So, but for these applications, induction is very superior than the cumulative. So, cumulative compound DC motor is used in high torque intermittent load cycles like shear metal punches, presses, crushers, some elevators, lifts, conveyors. But for these applications, induction is superior than the cumulative. So, this cumulative compound DC motor is basically used for high torque intermittent load cycles. So wherever there is a huge amount of torque applications and a sudden load of variations, there we are going to prefer the cumulative compound like load cycles like shear metal punches, pressers, crushers, some elevators, lifts and the conveyors. And but for these applications, induction is more superior than the cumulative. See, cumulative can be used, but out of this, induction is more superior than the cumulative for the sudden high torque. Wherever the load requires high torque with a sudden load variations, there we are going to use the cumulative, but induction is more superior than the cumulative. So in differential motor, I have already told you the torque is directly proportional to net flux into armature current. Net flux is equal to phi H minus phi SC. So as load increases, then IA increases, so phi SC increases, so overall flux will decrease. So therefore, the torque will decrease. As you can see clearly, the change, we can say that whatever the flux resultant is always more decrease when compared to this one. So overall value will decrease. So T will decrease. So therefore, it is a worst one. So finally we can say whenever the load increases, the IA increases. So therefore, phi SC increases. So overall flux decrease. The resultant flux decrease is very, very, very higher when compared to IA increase. So overall values will still decrease. So therefore we can say it is a worst one. So whenever the load increases, the torque will decrease for this differentiable motor. So N is directly proportional to EV by phi. EV is nothing but V minus IA into RA plus RSC by phi. The net flux is equal to phi H minus phi SC. As the load increases, IA increases. So phi SC increases. So therefore, the resultant flux will decrease. So this resultant flux change is very higher. So this value decreases means the overall speed will increase. So full load speed is greater than the no load speed in case of the differentiable motor. That is the reason the graph will be over the flat compound DC motor. So therefore it is a differential compound will have more speed when compared to the flat compound DC motor. These things are I've already shown you in the graph itself. So in a differentiable motor, torque is directly proportional to phi H minus phi SC into IA. As load increases, the IA increases, so phi SC increases, the resultant flux decrease. Phi SH minus phi SC is very higher when compared to current IA increase. So the torque will decrease. So it is said to be worst one. So whenever the load increases, the torque is decreased. So we can say it is the worst one. Always the torque should increase. Whenever the load increases, the torque must increase. But here it is a vice versa. So it is called as the worst case. And the speed is directly proportional to EB by phi. EB is nothing but V minus IA into RA plus RSC by phi is equal to phi H minus phi SC. As load increases, IA increases, so phi SC increases. So whatever this resultant value decreases very lesser is very high. So this decreases more high. So therefore overall value will decrease. So speed will, this value decrease means the overall speed will increase. So therefore full load speed is greater than the no load speed. So this is called as a full load speed. It is called as a full load speed is always greater than the no load speed. So therefore the graph is above the whatever the graph, the torque, the speed versus armature current, the graph will be above the flat compound DC motor. The speed control of DC motors. The speed control of DC motors are I've already told you N is directly proportional to EB by phi, is directly proportional to V minus IRA by phi. So the speed is going to depend upon the supply voltage, armature resistance and the field flux. So these are the three parameters. By changing changing these three parameters, we can get the value of the speed control. So N is going to depend upon the V, RA and also phi. See, phi is called as the flux control or field weakening control. So with phi is called as a flux control, basically it is also called as a field weakening control, and RA is called as the armature resistance control, and V is called as the voltage control. So constant torque means the load is always fixed. So these are the three methods by which we are going to control the speed of the DC motor, which is the V, the supply voltage control, armature resistance control and field weakening control. So these are the three methods by which we can control the speed of the DC motor, because speed is going to depend upon the V, RA and phi. So these are the three values on which speed is dependent. So with the help of these three parameters we can control the speed. So therefore here V is for the voltage control, supply voltage means the voltage control, RA is called as the armature resistance control and phi is called the flux control or field weakening control. The speed control of DC methods. The speed control methods of DC motors are N is directly proportional to EB by phi, is directly proportional to V minus IRA by phi. So it is going to depend upon supply voltage, armature resistance and flux. So phi is called the flux control or field weakening control, RA is called as the armature resistance control and V is called the voltage control. So if you vary the supply voltage, the speed you can control. If you vary the armature resistance, it is called as the armature resistance control. By that also we can control the speed. And phi is called as the flux control. By changing the flux also we can control the speed. So it is basically called as the field weakening control, and this is the armature resistance control and this is the voltage control. See, constant torque means the load is always fixed. See, in some questions they are going to give you constant torque. See, constant torque means the load is always fixed. That is the reason the torque is almost constant. So therefore the constant torque means basically the load is always fixed in nature. That is the reason we say it is said to be a constant load. So constant load, whenever the load is fixed, we say it is a constant torque. So constant torque means basically the load is always fixed. So constant torque means basically we say that the load is always fixed. So constant torque means basically the load is always fixed. So air has high reluctance. So core is used because it has very low reluctance in transformer. So air basically has the high reluctance. So core is used because it has the very low reluctance in transformer, because I have already told you in air the permeability of air is very less, so its reluctance is very higher. So whereas the core has a huge permeability, so its reluctance is less, because R is mostly proportional to permeability, because R is equal to L by mu into A. So the less the permeability, more is the reluctance, and more the permeability, less is the reluctance. So always flux tries to move in that region where the reluctance is very less. So therefore if you use the core, the total flux is going to be confined only in the core itself. So this is the important thing that we can say here. So therefore air has high reluctance, so core is used because it has the low reluctance in transformer. Short circuit ratio, SCR, short circuit ratio is equal to 1 by X per unit. So short circuit ratio SCR in a transformer is equal to 1 by X per unit. X per unit is called the per unit synchronous reactance. So the short circuit ratio SCR is nothing but it is 1 by X per unit, and simply it is called as the per unit synchronous reactance. So this is a very important formula. The short circuit ratio SCR is equal to 1 by X per unit. X per unit is called as the per unit synchronous reactance. So short circuit ratio SCR is equal to 1 by X per unit. X per unit means per unit synchronous reactance. So short circuit ratio of synchronous machine is equal to 1 by X per unit. X per unit is equal to per unit synchronous reactance. When a fault occurs, these things are going to happen. So whenever a shunt fault occurs, these things are going to happen. See, I is equal to V by X. As X decreases, current I will increase. Power factor is equal to P by S. As shunt fault increases, the power decreases. So therefore the cos phi decreases. And also the frequency will decrease. So therefore finally the current increases, the frequency decreases and the power factor decreases. So these are the things that are going to happen whenever a shunt fault is occur. So whenever a shunt fault is going to occur in the power system, so whenever a shunt fault is occurs, these things are going to happen, which is current is equal to V by X. So because whenever the fault is happening means the reactance will decrease. As the reactance decreases, simply the current will increase. And the power factor is equal to P by S. So power value will decrease. So therefore the power factor will decrease. And the frequency will also decrease. So these are the things which are going to occur whenever a shunt fault is occur, which is called as the current will increase, the power factor will decrease and the frequency will decrease. So these are the things that are going to occur whenever a shunt fault is occurring. So whenever a shunt fault occurs, current is equal to voltage by reactance. The reactance decreases, so therefore the current increases. And the power factor cos phi is equal to P by S. So power decreases, so the cos phi also decreases. The frequency also decreases. So therefore whenever a shunt fault occurs, the current increases, the power factor decreases and the frequency decreases. I have already told you AB is equal to Ki into 5 omega and also omega is equal to 2 pi n by 60 where n is called as the RPM. So torque is equal to Ki into 5 into Ia. So here K is same for both EB and T. So therefore simply we can say that EB is equal to Ki into 5 omega where omega is equal to 2 pi n by 60, n is in the terms of RPM and T is equal to Ki into 5 into Ia, which is same for both EB and K is same for both EB and T. So DC series motor field test is connected to determine the efficiency of traction motors. I have already told you for DC series motor we done the field test is connected to determine the efficiency of the traction motors, or simply we can say the DC series motor. So DC series motor efficiency can be figured out with the help of field test. So DC series motor its efficiency can be easily figured out with the help of this field test. So DC series motor for field test is connected to determine the efficiency of the series motor. Simply we can say a field test is connected on the DC series motor to figure out its efficiency. So field test is connected on the DC series motor to figure out its efficiency. So while keeping the excitation constant, if the steam supply of the alternator running with parallel another identical alternator is increased, then its portion of share in load will only increase and the other stays like that only. So while keeping the excitation constant, if the steam supply of an alternator running in parallel another identical alternator is increased, then its portion of share in load will only increase and the other stays like that only. See, it's a very important point. Suppose two alternators are connected in parallel. Suppose there are two alternators connected in parallel, they are identical. Suppose for one alternator I am going to increase the excitation, then definitely what is going to happen is the load shared by that alternator will increase, but the remaining alternator will never change its load. So whatever the load, the previous now also it is going to share the same load. As the mechanical input increases, the electrical output increases. So therefore we can say it is going to, the first alternator is going to share the more load, for the second one it will remain the same as the previous case. So simply we can say that while keeping the excitation constant, if the steam supply of an alternator running with parallel another identical alternator is increased, then its portion of share in load will only increase and the other stays like that only. So while keeping the excitation constant, if the steam supply of an alternator running with parallel another identical alternator is increased, then its portion of share in load will only increase and the other stays like that only. So while keeping the excitation constant, if the steam supply of an alternator running with parallel another identical alternator is increased, then its portion of share in load will only increase and the other stays like that only. Due to reduction of angular velocity of one machine, circuiting current will come into action when two alternators are operating in parallel. So due to reduction of angular velocity of one machine, circuiting current will come into action when the two alternators are rotating in parallel. See, I have already told you, whenever the two alternators are rotating in parallel, their voltage should be same. Suppose if one of the alternators is rotating at lesser speed, then the voltage will never be same. So voltage difference means circuiting currents are going to get produced. So due to reduction of angular velocity of one machine, circuiting currents will come into action when two alternators are operating in parallel, because whenever the two alternators are connected in parallel, their voltage should be same. If suppose they are going to rotate with different speeds, then voltage are also different, so certainly the currents are going to get present in that machine. So therefore, due to reduction of angular velocity, one machine circulating current will come into action when two alternators are operating in parallel. So due to reduction of angular velocity of one machine, circulating current will come into action when the two alternators are operating in parallel. A synchronous capacitor is an unloaded synchronous motor with overexcited condition, because at this condition it produces reactive power. I have already told you, a synchronous capacitor is an unloaded synchronous motor with overexcited condition, because at this condition it is going to produce the reactive power. I have already told you, the overexcitation, whether it is a synchronous motor or whether it is a synchronous generator, they are always going to generate the reactive power. They are always going to generate the reactive power. So therefore, at no load condition of synchronous motor, at the overexcitation, we can say that it is going to purely act like a synchronous capacitor, delivering the reactive power. A synchronous capacitor is an unloaded synchronous motor with overexcitation condition, because at this condition it produces a reactive power. So it is used for basically improving the power factor of the system, whereas at the under excitation, the synchronous motor at under excitation at no load, it is going to behave like an inductor. It is going to accept the reactive power. So therefore it can be used for the compensating the Ferranti effect. These things I have already explained in the synchronous machine concepts itself. So a synchronous capacitor is an unloaded synchronous motor with overexcited system, because at this condition it produces a reactive power. Transient stability studies of a power system are usually carried out over a time interval of first swing only. So transient stability studies of a power system are usually carried out over a time interval of first swing only. So therefore, the transient stability studies of a power system are usually carried out over a time interval of first swing only. So this transient stability studies means basically it is a study for the first swing itself. So whatever the transient stability studies means basically for a power system which are going to carry out over for a first swing, or for the first swing only we are going to carry out. The transient stability studies of a power system are usually carried out over a time interval of first swing only. So in the first swing only, if the studies which are carried out are called as the transient stability studies. So transient stability studies of a power system are usually carried out over a time interval of first swing only. If any disturbance occurred on the alternator, that is because of faults or any other. So if any disturbance occurs on the alternator, that is because of any faults or any other cases. See, disturbance in alternators is basically because of faults or any other condition. So basically disturbance are going to occur on the alternator whenever there is a faults occur on the power system. If any faults occur on the power system, it is going to directly produce a disturbance on the alternator. So whenever there is any fault occurs on the power system, definitely we can say that there is a disturbance occurs in the alternator. So whenever there is any fault in the power system, definitely there is a disturbance it is going to occur in the synchronous machine or alternator. So simply we can say that if any disturbance occurred on the alternator, that is because of any faults or any other case. So this is a very important point that you always need to keep to understanding. If the alternator is stable in the first swing, then it is also stable for the next swing also. So if the alternator is stable in the first swing, then it is also stable for the next swing also. I have already told you whatever the studies which are studied at the first swing is called the transient stability studies, and we can say if the alternator is stable for the first swing, then it is also stable for the other swings also. So if the alternator is stable in the first swing, then it is also stable for the other next swings also. In DC machines, the armature windings are placed on the rotor because of necessary for commutation. I have already told you, in a DC machines, the armature winding is always placed on the rotor because for the necessity for commutation. So because of the commutation process only, we always have to keep the armature winding on the rotor. In a synchronous machine, there is no need of commutation, so definitely we can keep the armature coil either on the stator or either on the rotor for synchronous machines. But in DC machines, commutation is always required. So that is the reason always we keep the armature winding on the rotor itself. So in DC machines, the armature winding are placed on the rotor because of the necessity for commutation. So basically commutation means, I have already told you, in the commutating time, whenever the the brush, whenever the brush is going from one computer segment to other computer segment, it is called as the computing time. In that time only, in that time basically, there is a short circuit for the coil, so current should reverse in that time itself. So whatever the current direction should change in that coil, and that as the short circuit, so we can say that EMF induced is equal to 0 there. So the current should basically change its direction in the time only. Otherwise, if it is not changing, means the spark is going to get occur. If it is changes in the time TC only, we say it is a successful computation. Otherwise, it is said to be an unsuccessful computation. The process by which current in the short-circuited armature coil is reversed while it crosses the magnetic neutral axis MN is called as a computation. I have already told you the process by which the current in the short-circuited armature, the process, or you can say the process by which the current in the short-circuited armature coil is reversed while it crosses the magnetic neutral axis is called as the commutation. The process by which the current in the short-circuited armature coil is reversed while it crosses the magnetic neutral axis is called as the commutation. The process by which current in the short-circuited armature coil is reversed while it crosses the magnetic neutral axis is called as a commutation. I have already told you, whenever the brush is moving from one computer segment to other computer segment is called as the commutating time. So in that time, the armature coil is going to get short circuited. So it has to change its direction from positive to negative direction. In the time only it should happen in the magnetic neutral axis. Otherwise, what is going to happen? Then definitely a spark is going to get occur. If it is happens in that time, then definitely we can say combustion is successful. Otherwise, we said the combustion is failure. So spark is going to get occur. The process by which current in the short-circuited armature coil is reversed while it crosses the magnetic neutral axis is called as the commutation. The fall in speed of a DC generator due to increase in load can be corrected by increasing the input to the prime mover. The fall in speed of a DC generator due to increase in load can be corrected by increasing the input to the prime mover. I have already told you, whenever the electrical load increases, so whenever the electrical load increases, the speed will decrease of the DC generator. Then we have to increase the speed by increasing the input to the prime mover. So whenever the electrical load increases, the speed of the DC generator will decrease. We have to increase the speed by using the input to the prime mover. If we increase the input to the prime mover, then definitely again the speed will increase. So the fall in speed of a DC generator due to increase in load can be corrected by increasing the input to the prime mover. So whenever the electrical load increases, we can say that simply, whenever the electrical load increases, the current IA increases. As the current IA increases, the electrical opposition increases. So electrical opposition increases means the mechanical torque and the electrical torque are opposite, and the electrical opposition increases. So therefore, the speed will decrease. So you have to increase the speed by giving more amount of steam. So this is a very important point. Whenever the electrical load increases, the current IA increases. As the current IA increases, the electrical torque increases. Electrical torque and mechanical torque are opposite of each other. So the speed will decrease. You have to give the input to the steam. So you have to increase the input to the steam. So therefore, the speed can be increased again. Ideally, the damping torque should be proportional to the velocity of the moving system, but independent of operating current. So ideally, the damping torque should be proportional to the velocity of the moving system, but independent of operating current. So this is a very important point. Ideally, the damping torque should be proportional to the velocity of the moving system, but independent of the operating current. So this is a very important statement. Ideally, the damping torque should be proportional to the velocity of the moving system, but independent of the operating current. So this is a very, very important point here. Ideally, the damping torque should be proportional to the velocity of the moving system, but independent of the operating current. So whatever the damping torque should depend only on the velocity of the moving system, but independent of the operating current. So we can simply say that ideally the damping torque should be proportional to the velocity of the moving system, but independent of operating current. So ideally the damping torque should be proportional to the velocity of the moving system, but independent of the operating current. Transformer core must have high permeability and low hysteresis losses. I have already told you the transformer core should have huge amount of permeability, so its reluctance will decrease. So more flux. See, flux always try to go in a region where the reluctance is very lesser. And the low hysteresis losses means we can say as the hysteresis loss decreases, the iron loss also decreases, because iron loss is a summation of hysteresis loss and the eddy current losses. As the hysteresis loss decreases, we can say simply the iron loss also decrease. So we need a core which has the high amount of magnetic permeability and the low amount of hysteresis losses. I have already told you the transformers has the fast voltage regulation and the lagging power factor and the negative voltage regulation at the leading power factor. So I have already told you, for lagging power factor, irrespective of the lagging power factor, the voltage regulation is always positive. Whereas for leading power factor, the voltage regulation can be positive, it can be negative, and it can be zero also. So this is the concept that you always need to keep in understanding this one. So stepper motors are used in printers. I have already told you the different types of applications of stepper motors. Basically, stepper motors means they are going to rotate in the terms of steps. So therefore, we can say it is used in the printers. The core of a transformer is made of silicon steel. I have already told you the steel has the very good permeability and also good conductance. But we need the conductivity to be very less because the currents are proportional to conductivity. So more is the conductivity, more is the current loss. So we have to reduce the conductivity. So for that we have to add the silicon for 3 to 4%. If we add this one, so the permeability will be same as the previous one. Only thing is we are going to increase the resistivity of the core. So therefore the current loss decreases. So if we add more than this 3 to 4%, the silicon is going to make the steel very brittle, means it can be easily broken. So therefore the core of the transformer is made of silicon steel. Aluminum is not used as winding wire for the armature of a DC machine because aluminum is not used as the winding wire for the armature of a DC machine because a large winding space is taken by aluminum conductors and creating jointing problems, and also the thermal conductivity of the aluminum is very low, and aluminum has low conductivity as compared to copper. That is the reason aluminum is never used as the armature winding in a DC machine, whereas always use the copper only. So aluminum is not used as a winding wire for the armature of a DC machine because a large winding space is taken by the aluminum conductors and creates the jointing problems, and the thermal conductivity of the aluminum is also very less, and the aluminum has low conductivity as compared to copper. So aluminum has low conductivity compared to copper, it has low thermal conductivity compared to copper, and it is going to occupy a more amount of space and it creates the jointing problems also. So these are the problems which are encountered by aluminum. So that is the reason we use the copper winding in the armature of a DC machine. So the aluminum is not used as a winding wire for the armature of a DC machine because a large winding space is taken by the aluminum conductors and creates the jointing problems, and the thermal conductivity of the aluminum is low, and the aluminum has low conductivity as compared to copper. So these are the points that you always have to keep remember. So therefore aluminum is not used as winding wire for the armature of a DC machine because a large winding space is taken by aluminum conductors and creates jointing problems. A thermal conductivity of the aluminum is low, and the aluminum has low conductivity as compared to copper. So therefore simply we can say that aluminum is not used as a winding wire for the armature of a DC machine because a large winding space is taken by aluminum conductors and creates the jointing problems, and the thermal conductivity of the aluminum is very less, and aluminum has low conductivity as compared to copper. The function of a brush and commutator segment in a DC motor is to produce the unidirectional torque. I have already told you the basic function of a brush and a commutator segment in a DC motor is to produce the unidirectional torque. So the basic function of a brush and also the commutator segment in a DC motor is to produce the unidirectional torque. See, this commutator segment is soldered to the winding, so therefore whenever the winding rotates, the commutator segments are also going to get rotated, but these brushes are always stationary. They are going to collect the current, or they are going to give the current to the commutator segments. So the function of a brush and a commutator segment in a DC motor is to produce the unidirectional torque. The function of a brush and a commutator segment and a commutator arranged in a DC motor is to produce the unidirectional torque. The function of a brush and a commutator segment in a DC motor is to produce the unidirectional torque. The transformer core is laminated to reduce the eddy current losses only. I have already told you the transformer core is laminated. The only agenda for doing this one is basically to reduce the eddy current losses only. The basic agenda for laminating the transformer core is basically which is for reducing the eddy current losses only, but not reducing the hysteresis losses. So simply we can say that the basic agenda of laminating the transformer core is only for reducing the eddy current losses only, but not the hysteresis losses. So transformer core is basically made of silicon steel. We are going to laminate this one to only to reduce the eddy current losses. And the IDMT relays are used to protect the transformer against the external short circuits. It's a very important question. IDMT relays are used to protect the transformer against the external short circuits. These IDMT relays are going to be used to protect the transformer against the external short circuits. So whenever there is external short circuits, current will be high, then we can, with the help of this IDMT relay, we can protect the transformer from against the external short circuits. So IDMT relays can be used to protect the transformer against the external short circuits. So these IDMT relays are used to protect the transformer against the external short circuits. It's a very important thing. So IDMT relays are used to protect the transformer against the external short circuits. So these IDMT relays are basically used to protect the transformer against the external short circuits. Given load torque, at a given load torque, speed of AC motor is lesser than the speed of DC series motor. I already told you it's an important thing. Always speed of DC motor is always higher than the speed of AC motor. So speed of DC motor is always higher than the speed of AC motor. So therefore, at a given load torque, speed of AC motor is always lesser than the speed of DC series motor. I already told you the speed of DC motor is always higher than the speed of AC motor. So at a given load torque, speed of AC motor is always lesser than the speed of DC series motor. I have already told you at a given load, if you keep a fixed load for AC and DC motor, definitely the speed of DC motor is higher than the speed of AC motor. So basically brushless DC motor is a synchronous motor and its torque speed characteristics are similar to DC motor. So basically brushless DC motor is a synchronous motor and its torque speed characteristics are similar to DC motor. These things I have already told you. So basically brushless DC motor is a synchronous motor and its speed torque characteristics are similar to a DC motor. Means whenever the load increases, the speed will decrease. So these are the characteristics similar to a DC motor. So therefore simply we can say the brushless DC motor is basically a synchronous motor and its speed torque characteristics similar to a DC motor, because whenever the load increases, the speed decreases. In case of DC motor, same thing is going to happen for a synchronous motor also. So therefore simply we can say that simply at a given load, so therefore basically brushless DC motor is synchronous motor and its torque speed characteristics are similar to DC motor. I have already told you eddy current loss is directly proportional to square the frequency whenever the flux density is constant. So therefore the eddy current loss is directly proportional to square of the frequency at constant flux density. So eddy current loss is directly proportional to frequency whole square at constant flux density. So as load increases, the speed of DC series motor decreases. As load increases, speed of DC shunt motor decreases. As the load increases, speed of cumulative compound motor decreases. As load increases, the speed of DC differential compound motor increases. See, I have already told in detail of each and every motor. I have already told you whenever the load increases, the speed of DC motor decreases. As the load increases, the speed of DC shunt motor decreases. As the load increases, speed of DC cumulative compound motor decreases. As load increases, the speed of DC differential compound motor increases. These things I have already told you. Always the cumulative compound motor graph is going to lie between the series and the shunt. And this differential is always above the shunt one. All these things I have already told you. So therefore, whenever the load increases, the speed of the DC series motor decreases, the speed of DC shunt motor decreases, and the speed of DC cumulative compound motor is also going to decrease. But the only thing is, the speed of DC differential compound motor is going to get increased. All the diagrams are also I have already shown you in the detail in the DC machines class itself. So therefore, the next point is the Portier triangle. The Portier triangle is always a right angle triangle. I have already told you in the Portier triangle. For the Portier triangle, we are going to see in the case of methods which are useful for calculating the regulation of an alternator. So the Portier triangle is basically a right angle triangle in the measurement of voltage regulation of three-phase alternator by using the ZPF method. I have already told you the different type of methods. One is called as the EMF method, ZPF method, ASA method. All these things I have already told you, like EMF method. So EMF method, MMF method, ZPF method and ASA methods. So EMF method, MMF method, ZPFC method and the ASA methods. So these are the four methods that I have already discussed to figure out the regulation of an alternator. So voltage regulation of an alternator. So this Portier triangle is basically right angle triangle. We are going to see in case of the ZPF method and also in the ASA methods. The Portier triangle is always a right angle triangle in the measurement of voltage regulation of three-phase alternator by using the ZPF method. So this Portier triangle is basically right angle triangle in the measurement of voltage regulation of three-phase alternator by using the ZPF method. Increasing order of voltage regulation of these generators is under compound, shunt and differentiable compound. Increasing order means small to big. I have already told you differentiable compound, it has huge amount of voltage regulation because no load voltage and the rated voltage are both very high, the distance is very high, so it is called as a differentiable compound. So increasing order means small to big. The voltage regulation of under compound is lesser than the voltage regulation of shunt is lesser than the voltage regulation of the differentiable compound. So this is a very important point that you always need to keep in understanding. The voltage regulation of under compound is lesser than the voltage regulation of shunt is lesser than the voltage regulation of the differentiable compound. These things I have already shown you in the graphs also. So therefore, the voltage regulation of under compound is lesser than the voltage regulation of shunt is lesser than the voltage regulation of differentiable compound, because no load voltage and the rated voltage has a huge amount of difference. So it is very higher for a differentiable compound. And here the under compound voltage regulation is lesser than the shunt. This generator is lesser than the differentiable compound generator. If phi m is the peak value of flux, then the magnitude of the rotating magnetic field will be, then the for two-phase supply which is phi m, and for three-phase supply it is 1.5 phi m. I have already told you, if phi m is the peak value of flux, then the magnitude of the rotating field magnetic field, the peak value of the magnitude of the rotating magnetic field is nothing but n by 2 into phi m. So n is the phase, then it should be always greater than 2 or greater than 2 only. We have to choose this one, or greater than or equal to 2. So for two phase we are going to get phi m, and for three phase we are going to get 1.5 phi m. See, I have already told you, where phi m is the peak value of flux, then the magnitude of the rotating field peak value, and the magnitude of the rotating peak value is nothing but for n phase system which is n by 2 into phi m, for n greater than or equal to 2. So for two phase system, this substitute n is equal to 2, we are going to get phi m. For three phase system which is 3, substitute here 3 by 2 is nothing but 1.5 phi m, which is for n greater than or equal to 2. This is the formula we are going to get. If phi m is the peak value of the flux, then the peak value of the rotating magnetic field will be, it is n by 2 into phi m for n phase system, n greater than or equal to 2. So this is the case that you need to always remember. So for two phase substitute n is equal to 2, we are going to get phi m. For three phase system n is equal to 3, we are going to substitute, we are going to get 1.5 phi m. Slip test is performed to determine the XD and XQ in a silent pole alternator. So slip test is basically performed to determine the XD and XQ in a silent pole alternator. So this XD and XQ are going to come only in the case of silent pole alternator. So then by the slip test we can figure the value of the XD and XQ. Slip test is performed to determine the XD and XQ in a silent pole alternator. So slip test is performed to determine the XD and XQ in the case of a silent pole alternator. And we already told you, XD is called as the direct axis reactance and XQ is called as the quadrature axis reactance. Damper windings are provided for starting torque and preventing the hunting in a three-phase synchronous motor. I have already told you the basic function of damper windings in a synchronous motor is to provide the starting torque and also to prevent the hunting. These things I have already told you. So therefore, see, hunting means basically, suppose if the rotor speed is greater than ns, the generating torque is going to get act which is opposite to the motor torque. So it is going to decrease its speed to the ns. Suppose due to sudden load, the speed is decreased. Due to sudden increase in load, the speed is decreased, which is nr less than ns. Then the inertial motor torque is going to get act, and this torque in the same direction of rotation. So the speed will be become equal to ns. So therefore, I have already told you the function of damper winding in synchronous motor is to provide the starting torque and also to prevent the hunting in a three-phase synchronous motors. So the damping windings are used for providing the starting torque and to prevent the hunting in a three-phase synchronous motor. Whereas in the case of synchronous generator, this damping windings can only prevent the hunting, and also it can also suppress the negative sequence components also. So negative sequence components present in the flux can be suppressed with the help of this damper windings in case of synchronous generator. All these things I have already told you. Magnetizing current in the three-phase supply lines of a three-phase transformer are sinusoidal. So therefore we can say the magnetizing currents in the three-phase supply lines of a three-phase transformers are sinusoidal in nature. So the magnetizing currents in a single-phase transformer is non-sinusoidal, but the induced voltages are sinusoidal. So these things are very important. The magnetizing currents in the three-phase supply lines of a three-phase transformer is sinusoidal, thus the magnetizing current in a single-phase transformer is non-sinusoidal, but the induced voltages are sinusoidal, because as the magnetizing current is non-sinusoidal, but the flux is sinusoidal. So therefore, if the flux is sinusoidal, EMF is also sinusoidal. So this is a very important point. In a single-phase transformer, basically the H curve is a non-linear. So therefore, the magnetizing current is a non-sinusoidal. Then definitely we are going to get a flux as basically sinusoidal. Or simply we can say with IM is peak waveform, we are going to get flux as sinusoidal. If flux is sinusoidal, definitely we are going to get the induced voltage also sinusoidal. Whereas the magnetizing currents in the three-phase supply lines, of a three-phase transformer are purely sinusoidal. Slip ring induction motor is a suitable motor for using the regenerative braking. So slip ring induction motor is suitable for motor for using the regenerative braking. So if you want the regenerative braking, then we go for the slip ring induction motor. So if you want the regenerative braking, then it is necessary to use the regenerative braking. So therefore, slip ring induction motor is more suitable for using the regenerative braking. So therefore, simply we can say that slip ring induction motor is more suitable for using the regenerative braking. If field winding in a DC series motor is open circuited, then initial speed is very high and then it is going to become the zero. See what is going to happen basically we can see that in a DC series motor, whenever the field winding is open circuited, as I already told you, whenever the field winding is open circuited, the armature current is equal to 0. So field flux is also equal to 0. As I have already told you, EB is directly proportional to N into phi. So therefore, N is directly proportional to EB by phi. As flux is equal to 0, then instantaneously the speed will be very higher and finally it is going to become 0. So therefore, initially the speed is very high and then later it's going to become 0. The torque angle characteristics of a 3-phase silent pole synchronous motor is a function of the torque angle characteristics of a 3-phase silent pole synchronous motor is a function of, which is P is equal to EV by X into sin delta plus V square by 2 into 1 by, which is X2 minus XD into sin 2 delta. So you can see clearly this is the equation that you are going to get, which is P is a function of sin delta and sin 2 delta. You can see clearly from this equation only that P is a function of both sin delta and also sin 2 delta. So the torque angle characteristics of a 3-phase silent pole synchronous motor is a function of P is equal to EV by X into sin delta plus V square by 2 into 1 by X2 minus XD into sin 2 delta. So P is a function of sin delta and also sin 2 delta. You can see clearly from this equation itself. So therefore, the torque angle characteristics of a 3-phase silent pole synchronous motor is a function of P is a function of basically sin delta and sin 2 delta. So P is equal to EV by X into sin delta plus V square by 2 into 1 by X2 minus XD into sin 2 delta. So P is a function of sin delta and sin 2 delta. Buchholz relay is connected between the conservator and the main transformer tank. So Buchholz relay is going to connect between the, it is a basically relay, it's a gas activated relay. It is basically a gas activated relay. It is going to connect in between the conservator and the main transformer tank. So whenever there is any internal fault, definitely because of this heat generated in this oil, a gas is going to get produced. So this gas is going to get sensed by this Buchholz relay and it is going to give an alarm that the fault is going to get happen. So this is the speed versus torque. The speed torque characteristics of a 3-phase synchronous motor with a damper winding. So this is the graph that you are going to give, which is the speed with respect to torque graph. So whenever the speed increases, the torque is also increases. It is directly proportional. So this is the case of a 3-phase synchronous motor with damper winding. So this is the speed torque characteristics of a 3-phase synchronous motor with the damper winding. So this is said to be a speed torque characteristic of a 3-phase synchronous motor with the damper winding. This is the speed versus torque graph. So speed torque characteristic of a 3-phase synchronous motor with damper winding. In DC generator with lap connected winding, the number of brushes always equal to number of poles. I have already told you, irrespective of the lap winding, I have already told you the number of parallel paths is equal to number of brushes that we are going to require. The number of parallel paths means the number of brushes are going to get required, or simply the number of brushes are always equal to number of parallel paths. In case of lap winding, the number of parallel paths is equal to number of poles. So therefore, the number of brushes required the lap winding is equal to number of poles. Similarly, in this generator with wave connected winding, the number of brushes is equal to 2 for small rating machines and it is equal to P for large rating machines. I have already told you one important point, which is here in a DC generator. In a DC generator with a wave connected winding, the number of parallel paths are 2. So therefore, the number of brushes is equal to 2 for smaller rating machines, but it is equal to P for larger rating machines. So this is a very important point that you always have to keep remembering, which is here the number of parallel paths is equal to number of brushes which are required. So the number of brushes are always equal to number of parallel paths. So in case of lap winding, the number of brushes is equal to P, whereas in case of wave winding, the number of brushes is equal to 2. For small rating machines, for large rating machines of wave winding, the number of brushes is equal to P. So P, so if wave connected for small rating machines, the number of brushes is 2 and it is equal to P for large rating machines. Under short circuit condition of alternator, only inductive reactance is present. So the power factor is almost zero lagging and the armature reaction is purely degradation. This concept also I have already told you. Under short circuit condition of alternator, only inductive reactance is present. So the power factor is almost zero lagging and the armature reaction is purely degradation. See, these things I have already told you. If you do the short circuit, or you can say, if you do the short circuit of the alternator terminals, the armature terminals, then definitely we can say that the synchronous impedance is purely, we can say this, it is almost inductive reactance. So we are going to get only inductive reactance. So power factor is almost zero lagging. So therefore we can say that in alternator, for zero power factor lagging, the armature reaction is almost purely demagnetization. So this concept I have already told you in the synchronous machine concept itself. The phase sequence of voltage generation in the alternator can be reversed by interchanging any two of its phase terminals. The phase sequence of voltage generation in the alternator can be reversed by interchanging any two of its phase terminals. I have already told you here, if you interchange any of the two phase terminals, then definitely the phase sequence of the voltage generation is also going to get changed in terms of alternators. So the phase sequence of voltage generation in the alternator can be reversed by interchanging any two of its phase terminals. So if you interchange the supply to any phase 2 terminals, then we can change the phase sequence of the voltage generation in an alternator. The phase sequence of voltage generation in the alternator can be reversed by interchanging any two of its phase terminals. The phase sequence of the voltage generation in the alternator can be reversed by interchanging any two of its phase terminals. So if you interchange any two phase terminals, the supply phase sequence, then you can overall change the phase sequence of the voltage generation in the alternator. So therefore finally we can say that the phase sequence of voltage generation in the alternator can be reversed by interchanging any two of its phase terminals. Synchronous impedance method gives the voltage regulation more than the actual value. So this is called as a synchronous impedance method. So synchronous impedance method gives the voltage regulation more than the actual value. I have already told you there are different types of methods to figure out we can say the voltage regulation of an alternator. Out of that, the synchronous impedance method. The synchronous impedance method, which is going to give you the voltage regulation more than the actual value. And I have already told you which one is more accurate and which one is going to give you the higher values also. I have already discussed in a very detailed manner. So we can see that the synchronous impedance method, it is a type of method which is going to measure the voltage regulation of an alternator. It is going to give you the voltage regulation which is more than the actual value. And the advantage of the damping torque in synchronous motor is to provide the hunting and also to provide the starting. As I already told you, the advantage of the damper winding in the synchronous motor is to make the two functions. One is to provide the hunting and also to provide the starting torque. Hunting is basically, see, if I increase the load on the synchronous motor, the speed is less than synchronous speed. So therefore what is going to happen is the induction motor torque is going to get happening the same rotation. So therefore the speed will increase to ns. Similarly, due to low load, the rotor speed, suppose it is greater than ns, then induction generator torque is going to get act. It is opposite to the rotation of the rotor. So therefore now speed will decrease and it will make to nr is equal to ns. So this is called as the hunting. So whenever is any second change in load, the speed is going to get changed, and with the help of this damper winding we can get back to the original speed. So this is the advantage of the damping torque. In a synchronous motor it can do two functions. One is to provide the hunting and the other is to provide the starting. The number of commutator segments is equal to number of coils in double layer winding. Number of coils is equal to number of slots. I have already told you the number of commutator segments is equal to number of coils irrespective of the type of winding. I have already told you this important point. The number of commutator segments is equal to number of coils on the armature irrespective of the type of winding, whether it is a lap winding, whether it is a wave winding, or whether it is a progressive winding or whether it is a retrogressive winding. Irrespective of the type of winding on the armature, always the number of commutator segments is always equal to number of coils. I have already told you in a double layer winding. See, suppose, let me take a small example. Suppose there are, in a double layer winding, suppose if there are 30 coils. Suppose let me assume there are 30 coils. 30 coils means I have already told you 30 coils will have, for each coil will have 2 coil sets. So therefore 30 into 2 is nothing but 60 coil sets. So therefore now I have already told you in a double layer winding we have to keep the 2 coil sets in one slot. So therefore 2 coil sets in one slot means 60 coil sets we can keep in 30 coils. in 30 slots. So therefore we can say that the 30 slots we are going to keep. So therefore you can see clearly there are 30 coils and there are 30 slots. So therefore the number of coils is equal to number of slots in the double layer winding. And I have already told you, irrespective of the type of winding, always whether it is single layer winding, whether it is a double layer winding, whether it is a lap winding, or whether it is a wave winding, or whether it is a progressive winding, or whether it is a retributive winding, always the number of commutator segments is always equal to number of coils in the armature irrespective of the type of the winding. Only in the case of double layer winding, the number of coils is always equal to number of slots. So crawling in squirrel cage induction motors is tendency to run at stable at speeds as low as 1/7 of the synchronous speed. In induction motor, harmonics are produced. Because of this, harmonic torque is produced. See, I have already told you, crawling is basically means it is a squirrel cage induction motor is a tendency to run at a stably at speeds as low as 1/7 of the synchronous speed. So in induction motor, harmonics are produced. Because of this, harmonic torque is going to get produced. I have already told you one important point. Crawling is nothing but the rotor is going to run at a speed which is nearly equal to ns by 7th speed, which is a very low speed. It may be because of the harmonics in the flux generation, because whenever the stator and the rotor, if there is no slots, whatever the flux distribution between them will be pure sinusoidal. But if there are slots in the stator and also in the rotor, definitely the waveband will be not pure sinusoidal in the air gap, so it will have some harmonics also. So because of this harmonics only, we are going to produce the harmonic torques are also going to get produced. So because of that, overall the torque versus speed graph is going to get little bit changed. So because of that, even at the higher slip ratings, we are going to get a stable region, and because of that only, it is going to operate at a very low speed. Low speed means slip is very higher. So therefore we can say that simply because of this harmonics only, the harmonic torques are going to get produced. So therefore the overall torque and the speed graph is going to get changed from the original thing that we have studied. So therefore even at the less speed, which is higher slip, the motor is going to behave like a stable region. So this is what we are going to get. So therefore crawling in squirrel cage induction motor has a tendency to run stably at the speeds as low as 1/7 of the synchronous speed. In induction motor, harmonics are produced. Because of this, harmonic torque produces. Shunt generator develops a stable output voltage. So if modulation characteristics is non-linear, I have already told you one important point. Shunt generator develops the stable output voltage if modulation characteristics is non-linear. I have already told you the modulation curve is always non-linear, means the OCC graph is always non-linear. Then only there is an intersection of EF is equal to IF into RF and this OCC graph. Then only we are going to get a stable output voltage. So shunt generator develops the stable output voltage if the modulation characteristics is non-linear, means the OCC graph is non-linear. Then only we are going to get a stable output voltage. So shunt generator develops the stable output voltage if the OCC curve or the modulation curve is non-linear. Then only we can say that this OCC curve and the modulation curve and the EF is equal to IF into RF are going to get intersect, and then we are going to get a stable operating point. So in a differentially compound DC motor, the speed falls non-linearly as the torque increases. These things I have already told you here. In a differentially compound DC motor, the speed falls non-linearly as the torque increases. See, these things I have already told you. For each and every motor, I have shown the graph with respect to speed and also torque. So therefore we can say the speed is going to fall non-linearly as the torque increase for the differentially compound DC motor. So therefore I have already told you very important point. Suppose the load is increased in a differentially compound DC motor. Suppose whenever the load is increases, so whenever the load increases, the armature current increases. So therefore phi SC increases. So overall flux decreases. So definitely we can say that the speed is going to get in a differentially compound DC motor, the speed falls non-linearly as the torque increases. So this is what that we are going to get in case of the differentially compound DC motor. In a three-phase induction motor, under locked rotor condition, I have already told you NR is equal to 0, so S is equal to 1. So large voltage induced at the rotor frequency. So large voltage is going to induced at the rotor frequency because Fr is equal to S into Fs, as S is equal to 1. So rotor frequency is equal to supply frequency. So the three-phase induction motor under the locked rotor condition, NR is equal to 0, S is equal to 1. So large voltage induced at the rotor frequency. Whenever the S is equal to 1, the S into S into E2 value is also large because S is equal to 1, E2 is again 1 into E2, E2 is nothing but E2. So whenever under locked rotor condition, S is the higher value, so their product S into E2 is also higher value. So you are going to get a large voltage induced at the rotor frequency is equal to supply frequency itself. Actually, this has to be large voltage induced at the supply frequency. It should be always supply frequency because you have S is equal to 1, so therefore FR is equal to Fs. So we should actually, they should mention here large voltage induced at the supply frequency. So in two revolving field theory, one field rotates in the forward direction with the slip yes, and the other field rotates in the opposite direction with the slip. I already told you the forward slip is S means the backward slip is 2 minus S. The equivalent rotor resistance R2 dash component in the equivalent circuit of a single phase induction motor is here R2 dash by 2S for the forward field rotation, whereas R2 dash by 2 into here backward slip which is 2 minus S. So therefore here we are going to make this R2 dash into two components, which is R2 by 2, and also here actually here it will be in the equivalent circuit diagram there will be R2 dash by S. So we are going to split into two parts, which is R2 dash by 2SF and R dash by 2SB. SF is nothing but forward slip is equal to S and the backward slip is equal to 2 minus S. So like this we are going to get. So this is a component for the forward rotation and this is for the backward rotation. So therefore in two revolving field theory, one field rotates in the forward direction, the forward slip is equal to S, and the other field is going to rotate in the opposite direction with a backward slip of 2 minus S. The 2 minus forward slip is equal to 2 minus S. The equivalent rotor resistance R dash component in the equivalent circuit of a single phase induction motor is, I have already told you, in the equivalent circuit diagram we are going to get R dash by S. So we are going to split into two parts, which is R2 dash by 2SF and R dash by 2SB. SF is equal to S and SB is equal to 2 minus SF is equal to 2 minus S. So we are going to get like this. So this is the component for the forward field rotation and this is the component for the backward field rotation. The reluctance power and reluctance torque of a three-phase silent pole synchro generator is the reluctance power and the reluctance torque of a three-phase silent pole synchronous generator is, which is P is equal to V square by 2 into 1 by XQ minus 1 by XD into sine 2 delta. So P is equal to T into omega, so T is equal to P by omega. So finally we are going to get V square by 2 omega into 1 by XQ minus 1 by XD into sine 2 delta. So this is the equation that I have already told you, which is P. This is T is called as the torque. See the torque in the reluctance torque in a three-phase silent pole synchro generator. This formula I have already told you, T is equal to V square by 2 omega into 1 by XQ minus 1 by XD into sine 2 delta. So P is equal to T into omega. So P is equal to T into omega. If you do the 2 into omega, you are going to get the expression of the power. So XD is called as the direct axis reactance and XQ is called as the quadratic axis reactance. This formula I have already told you, the torque is equal to V square by 2 omega into 1 by XQ minus 1 by XD into sine 2 delta. So P is equal to T into omega. You know the value of T. So multiply T with omega, you are going to get the power P, which is V square by 2 into 1 by XQ minus 1 by XD into sine 2 delta. So this is called as the reluctance power of a three-phase silent pole synchronous generator, and this is the reluctance torque of a three-phase silent pole synchronous generator. XD is called as direct axis reactance and XQ is called as the quadratic axis reactance. See, parallel connected transformer share load proportional to their KVA ratings. These things I already told you. In a parallel connected transformer, they are going to share the load proportional to their KVA ratings. So more is the KVA rating of the transformer, it will share the more load, and less is the KVA rating of the transformer, it will share the less load. So parallel connected transformer share load proportional to their respective ratings. So parallel connected transformer share load proportional to their respective ratings. So parallel connected transformer share load proportional to the KVA to their respective ratings. More is the rating of the transformer, it will share the more load. Less is the rating of the transformer, it will share the less load. The main application of delta zigzag connected three-phase transformer is to supply the unbalanced load. This concept I have already explained in detail in the previous classes only. So therefore the main application of delta zigzag connected three-phase transformer is to supply the unbalanced load. So therefore here the main application of delta zigzag connected three-phase transformer is to supply the unbalanced load. So therefore the main application of the delta zigzag connected three-phase transformer is to supply always the unbalanced load. The main application of delta zigzag connected three-phase transformer is to supply the unbalanced load. So this is the main application of the delta zigzag three-phase transformer. So it is always going to connect a unbalanced load. It is going to give a supply to the unbalanced load. So therefore the main application of the delta zigzag connected three-phase transformer is to give supply to this unbalanced load. So this is the basic principle or main agenda of this delta zigzag connected three-phase transformer. It is always going to give a supply to the unbalanced load. So therefore the main application of the delta zigzag connected three-phase transformer is to always give the supply to the unbalanced load. The regulation of a single phase transformer is, I've already told you, the maximum regulation that you are always going to get only at the lagging power factor. Then the power factor, the tan phi is equal to SEQ by REQ. This is the at the lagging load. I've already told this important point. So only at the lagging load you are going to get the maximum voltage regulation, which is tan phi is equal to XEQ by REQ, where XEQ is called as the equivalent reactance and REQ is called as the equivalent resistance. And if you want to find what is the minimum voltage regulation, it is of a single phase transformer, which is just to do the reverse of this one, which is tan phi is equal to REQ by XEQ. Just to the reverse of this, we are going to get like this, which is tan phi is equal to REQ by XEQ for the leading power factor load. So this is a very important point. I already told you at the lagging power factor load, always the voltage regulation is always positive, whereas for the leading power factor load, the voltage regulation can be positive, the voltage regulation can be negative, the voltage regulation can be 0.